welcome you today to this event convened by Academia 2063 to mark the official launch of Africa Agriculture Watch, for short AGWA, as its fourth core program. So this session today will be themed leveraging artificial intelligence and satellite remote sensing data for decision-making in the African agricultural sector. And I can promise you from the lineup of speakers we have planned, nothing short of a rich and exciting conversation. So be part of it, be an active participant. Head to the chat, tell us your name, tell us your organization, tell us where you're joining from and what you hope to see during this conversation. And throughout this event, please head to the Q&A if you have any questions, reflections, contributions that you would like to be discussed during the session. And of course, during the Q&A segments, you will have the possibility of raising your hand if you wish to intervene live, and you will be given the floor. As always, we are providing simultaneous interpretation in English and French. If you need interpretation, please look at the bottom of your screen and click on the button interpretation, and there you can choose English or French. We are equally live streaming on Academia 2063's YouTube channel. Now that the housekeeping is out of the way and now that we are all fired up for this exciting conversation, it is my pleasure to welcome the chair of today's session, Ambassador Extraordinary and Plenipotentiary of the Gambia to Switzerland and Permanent Representative to UN organizations in Geneva, the World Trade Organization, and other international organizations. He is equally an esteemed member of the Malabo Montpellier panel. Please welcome His Excellency Professor Muhammadu M. Oka.
Thank you. Thank you. Good morning, delegates and participants. It is indeed an honor to welcome you all this morning on this very, very timely and important event. Delegates and participants, Africa's food production systems constantly battle numerous threats, including climate shocks, conflicts, health crises, plant diseases, and pest outbreaks. The disruptions engendered by such crises require accurate and timely data generation to predict and inform agricultural production for better preparedness and intervention planning. However, such data analytics with predictability capabilities is not always readily available to our decision makers across our continent. In response to the agricultural data gap across Africa, Academia 2023 developed Africa Agricultural Watch, which we call AGWA. This was launched in 2021. AGWA is a web-based platform that employs cutting-edge machine learning techniques and satellite remotely sensed data to predict agricultural yields and production levels of several crops across Africa to support decision-making, monitoring, crisis management, and effective intervention planning in local communities. Against this context, Academia 2063 is hosting this event to mark the official launch of the AGWA program. This event will facilitate high-level stakeholder engagement around the use of artificial intelligence and emerging technologies to drive agricultural productivity and strengthen resilience across Africa for better crisis preparedness in the face of shocks such as the Russia-Ukraine war and COVID-19, and many others that may come our way. We are delighted and honored to be hosting you via this virtual platform under the theme Leveraging Artificial Intelligence and Satellite Remote Sensing Data for Decision-Making in the African Agricultural Sector. I'm indeed honored to serve as your chairperson and will be moderating the sessions. This event mobilized distinguished participants and policymakers, research organizations, farmers organizations, development partners, and think tanks, among others, to deliver and engage with us on the following specific objectives. One is to assess and reflect on the state of agricultural data availability in Africa and challenges and opportunities for data generation and use. Two, analyze AGWA's value proposition and discuss how the web platform is facilitating access to agricultural data while leveraging artificial intelligence and other emerging technologies to fill the data gap. Three, delve into the AGWA scope of intervention, touching on remote sensing, artificial intelligence in agriculture, and artificial intelligence in climate adaptation and mitigation. Four, we will also discuss opportunities for better policy outcomes across Africa as a result of evidence-based decision-making facilitated by AGWA's crop production forecast. And lastly, five, engage with leading experts, practitioners, and policymakers in artificial intelligence, agriculture, and climate. So with this backdrop, I'm delighted and honored to welcome our distinguished speakers that include our distinguished Executive Chairperson of Academia 2063, Dr. Ousmane Badiane. And we will also be joined by Dr. Jeffrey Bahligwa, the Director, Department of Agriculture, Rural Development, the Blue Economy and Sustainable Environment at the African Union Commission. We will also be joined by Dr. Rasin Lee, the Director and the Department of Data Management, Digital Products and Technology at Academia 2063. We also have among our midst Professor Martin Brand, who is an Associate Professor at the Department of Geoscience and Natural Resources Management at the University of Copenhagen. We will also be joined by Madam Madeleine Diouf-Sarr, who is the head of the Climate Change Division at the Ministry of Environment, Sustainable Development, and Ecological Transition in Senegal. We will also have Mr. Zi Guo, who is the Senior GIS Coordinator at the International Food Policy Research Institute, IFPRI. And we will also have Dr. Parmez Shah, who is a Global Lead for Rural Livelihood and Agricultural Jobs at the World Bank. And finally, and not the least, Dr. Mohamedou Bamba Silla, who is the Ames Canada Research Chair in Climate Change Science at the Ames office in Rwanda. We will also have Dr. David Laborde Dubuquet, who is the Director, Agricultural Economics Division at the Food and Agriculture Organization of the United Nations, FAO. We'll also be joined by Professor Benjamin Lamti, who is a visiting scientist at the West African Science Service Center on Climate Change and Adapted Land Use, WASCAL. Dr. Ismahin Ilowofi, who is the Chief Scientist at the Food and Agriculture Organization of the United Nations, and as also Mr. Hassan Nyambi, who is the Director of Sustainable Development and Blue Economy at the African Union Commission. As you can see, we have quite a distinguished lineup of thought leadership around policy, around research, and around field work among our midst here today to engage us. Welcome to you all, and we look forward to your interventions. I will now hand over to Dr. Ousmane Badiane, the Executive Chairperson of Academia 2063, to give his welcoming remarks. Dr. Badiane, you have the floor. You can unmute.
Thank you, Your Excellency, Ambassador Ka. It's a pleasure to always see you, and thank you for making time for us to join us here today. Let me also send a warm greetings and welcome to all those who are joining us here from across the globe for the formal launch of the Africa Agriculture Watch platform at Academia 2063. You alluded to that, Professor, in your introductory remarks. the issue of data, and it's important for the development process. We know that across the globe, and looking back in history, development is not a straight line. We move and we jump across periods and achieve huge advances in different areas. And that's how the growth process is boosted and sustained and accelerated. In the context of data analytics and managing that same development process in Africa, we have opportunities to see these jumps take place. And these jumps can be in so many different areas where we're facing huge challenges, but also considerable opportunities. If you think about the African economies trying to speed up the growth process, to broaden growth, to change livelihoods, there are so many different fronts to tackle so many different issues that anything that can allow us to cut through the infrastructural obstacles, the institutional bottlenecks, the technical constraints that we have, anything that allow us to jump in those areas will help us speed up growth and broaden the growth process. If you just think about a simple example, setting up an extension service, by the time you build the stations, the roads, hire the people, set them where they need to be, have them resourced, all of that takes time, all of that takes money. So are there any ways of cutting corners, doing things faster, reducing the time investment and the money investment? In the area of data and analytics for more impactful policies, for better development outcomes, there is no other opportunity around to leapfrog, to see those jumps take place than in the area of remote sensing and artificial intelligence today. How many African countries struggle with just knowing the area that has been tilled? How many African countries do struggle just to know what the yields are, what the production is? How many African countries struggle with just knowing how well the harvest season is going? All those are long-standing problems that we can solve today, and AGWA is a big contribution to that. When it comes to the innovations in data, in particular remote sensing and AI, Africa does not have to follow. We can lead from within. The telecom revolution has shown how much you can achieve if you put in the efforts and the resources. I remember a discussion with one of the former Minister of Telecommunications in the early 90s, and in the most advanced African countries actually, telling me that African countries were scared and terrified that the telecommunication information revolution was going to go just past by Africa, just zipping and developing other parts of the world. And here we are today. That is the area where Africa is the most competitive compared to the rest of the globe technically. So things are possible and we don't have to follow, we can lead from within. And that's where what comes in, that's where Academia 2063 comes in. We are investing in the data and the analytics for development and making that access to most African countries, if not all, and in a much larger and differentiated scale for different categories of stakeholders. AGWA actually was triggered by our response to the COVID crisis. There we were in February 2020. We had lockdowns, supply chains were all disrupted, and we had no clue what was going to happen to our production sectors. Were we going to be just sitting there and wait until the end to know whether farmers have gone to the farm, have not gone to the farm, have sold their seeds before the season, have maybe sold their assets, maybe were sick, worked part-time? We had no clue. We're just going to be hit straight in the face with whatever we had in terms of harvest, and then we'll have to deal with that. That's when we decided to set up a team which currently consists of 5 engineers, machine learning specialists, and IT people that are dedicated to this work full-time. And that's how we've been able to achieve what you'll be hearing about here today was going to be presented. Today, we talk about crop data, projections, and you'll hear from Dr. Lee. Way before the harvest, we can let countries and farmers and private sector operators know at pixel level, at district level, at regional level, country, national level, what to expect in terms of harvest so they can get prepared and respond if they need to. We are gearing up very soon to go into greenhouse gas emissions measurement and tracking. We are going to go into soil nutrients and crop mapping to allow our countries to plan better, to implement better, and hopefully to get better development outcome for everybody. So thank you to everybody who is joining us here today for your time and for your contribution. And let me hand over to the chair, just by saying to him that Dr. Godfrey Bayekwa is in a session to present a budget at the African Union for his department. If he's not on now presenting that, doing that, he will be joining us, so you can call upon him. Thank you very much to everyone.
Thank you, Usman, for that insightful welcoming remarks that actually set the stage for our engagement today. Dr. Bagwa will join us later on, so we'll move straight to the keynote presentation. I will now call upon Dr. Racine Lee, our director at the Department of Data Management, Digital Products and Technology at Academia 2063, to deliver the keynote presentation on the topic, AGWA, Leveraging Artificial Intelligence and Satellite Remote Sensing Data for Decision-Making in the African Agricultural Sector. Dr. Lee, you have the floor.
All right, thank you. Thank you so much, Prof. Ka, Your Excellency. I hope you can see my screen.
Yes, we can. Yes, we can.
All right, thank you. Thank you so much. So good morning, everybody. My name is Racine Lee, and I'm working at Academia 2063 as the director for the Department of Data Management, Digital Products and Technology. I'm going to present what the Africa Agriculture Watch platform is about as a 4th core program at Academia 2063. I will start my presentation by sharing a few key messages. As we know today, the Africa agricultural sector is facing numerous threats. You just named them, from conflict, extreme climate events, and health crisis. And here I'm mentioning the COVID-19 crisis. And all of those crises, what they have in common is the need for good planning and preparedness to reduce uncertainties when it comes to decision-making. For decision-making, if we rely on conventional data gathering and analytics techniques, that might not help us to deliver the level of details that is required given how the continent is very prone to crisis, but also in terms of frequency at which they occur, and for us to have an efficient intervention planning. What we witnessed recently is the efficiency that satellite remote sensing can bring on the table and help to reduce the data gap in the agricultural sector, but also how machine learning can allow to learn hidden patterns for predictions and also more analytics. The whole purpose for the Africa Agriculture Watch is to combine those two technologies and to disseminate data and analysis supports decision-making in the sector. And the presentation today is going to walk you through the different steps that we followed to develop the AFCP model, which is the Africa Crop Production Model, but also how we embed the outputs of the model within a platform to increase its outreach among stakeholders. My presentation today is a 5-fold presentation. I will be talking about an anatomy of decision-making just to set the scene and explain where the AGWA platform and program is coming from. And from there, we will have 2 stops. The first one is, what do we mean by enriching the input data with satellite remote sensing data? And the second one is the way we leverage predictability that is a key aspect when it comes to decision-making. And further, I will explain the AGWA conceptual framework, and from there, the AGWA main and upcoming products that has been already mentioned earlier by His Excellency and also Dr. Osman Bajani. I would like to start with the AGWA overarching goal. Here, if you see the pyramid, it's going from predictions all the way to society. The way we see this pyramid is the importance of predictions to make the invisible visible and allow to navigate through uncertainties. And from there, decision-making can be improved through those predictions, and we embed those models within a web-based platform to allow policymakers and deciders to have access to those outputs and strategize without having to bear the cost of going into technicalities, and hopefully to have a greater impact in society through policies. So this is the way we are thinking about how to improve the data access and also analytics in the agriculture sector through AGWA. I will maybe see now when it comes to decision making. This graph is a way of explaining the process of decision making that will usually start with an input data. From there, the input data, there are three elements, key ingredients that are important when it comes to taking a decision, which is a judgment, the predictions, and also the training. The judgment and the training are more subjective and depends on individuals or also agencies or entities. And predictions are more based on our experience. And nowadays, they are really relying on analytics and mathematical formulations. Based on those three ingredients, an action is taken and hopefully to have the right outcome. But at the outcome level, there is a feedback loop that can go back to the judgment and go back to the training to improve the way we consider each situation. And it can go all the way to the input data to now change the way and the type of data that will be collected to improve the whole system. For example, here, a simple example is when the input data is you wake up in the morning as a farmer, for example, you look at the field and you look at the sky based on your judgment, which is common knowledge or indigenous knowledge. Based on your training, your experience, you can predict that what am I feeling right now, given the wind, given the speed of the wind, given the sky, how cloudy it is, and the season we are in. I'm predicting that today it might rain. So the farmer might take an action and the outcome is hopefully the one that he or she will expect. So now what we are trying to do here is to show with this graph is that the more comprehensive the input data is, the better the process, because the input data is the entry point of taking a decision. We take a decision when we are facing a situation, and if there is no situation, there is no decision to take. So the more information we have about what is going on, the better it is. But another aspect that I wanted to show here is how predictions are at the heart of decision making and how important they are in our daily tasks and daily decisions. And also to show that predictions can be improved for decision makers to add value to that. So the whole purpose of AGWA is not to say that predictions will be leading the process of taking a decision, but how can we improve the predictions for decision and policymakers to use their judgment and training and their understanding of the situation to add value to those predictions and take better actions and hopefully having the right outcome. Now, I will be first with this slide. What AGWA is trying to do is to focus on those two first elements, the input data, using satellite remote sensing or adding the value of satellite remote sensing data, and also the prediction side, which is more about artificial intelligence, and in this case, machine learning algorithms. Now, when it comes to the data, there is a publication that is shared there that is the state of data availability in Africa. And the second map is the data capability in Africa. So we can clearly see in the first map that several African countries don't have a high score in terms of data availability. But when it comes to data capability, which means the capacity for the country to generate data, they all have pretty high scores. So the gap between the two is showing that there are barriers that need to be solved. And there, our stake at this is that the emerging technologies such as remote sensing can help to reduce that data gap between availability and capability. So here we at Academia 2063, when it comes to the Africa Agriculture Watch program, we rely on satellite images when it comes to contributing to enrich the data, the input data in the decision-making process. When you look at the first figure number 4, it's a raw RGB main image from Sentinel that have been processed, but the sub-image is the near-infrared counterpart. From this image, nothing can be said unless maybe expect that we can see croplands based on the shape and the greenness, and also the knowledge of the country. This is in Senegal. And the second graph, figure number 5, is the same image but processed, where we compute the normalized difference vegetation index as a proxy of how healthy or the level of photosynthetic activities that are happening there. So here, what we want to show is that satellite images can actually help to cover a large area with a few images, but also how it can also help us to have additional information by exploring the entire length and depth of the data when it comes to spatial resolution, but also spectral signatures. On the other hand, when you look at figure 6, it's something similar, a regular image, a true color, red, green, blue, seen in northern Egypt. We can clearly see also these are actually croplands, but no one can tell us right now what type of crop is there. It is green, but everything is green. It can be maize, it can be millet, it can be what have you. But by using machine learning techniques also, we can actually at least add value and bring an additional layer of information to increase the explainability of the map. So here we applied an unsupervised classification, and there we can start to see clusters by pixel in terms of similarities. So pixels that have the same signature will be grouped together, and it means potentially that each cluster is potentially a specific crop. So another advantage why we are using satellite images is that we can have the same scene several times in a year. That allows actually to monitor the change through time. And such an aspect is a game changer itself, because it allows actually to see how things are changing on the ground. When it comes to agriculture, for example, looking at crop rotations, looking at crop phenology metrics, where are we in terms of crop growth stages? All of those analytics become possible once we combine remote sensing data with more analytics, such as machine learning. When we go further in trying to explain what we mean by remote sensing data, and I talked about spectral signatures. The idea of spectral signatures is that each object on Earth will have a specific way of reflecting the sunlight. And that depends on the structure of that object, the orientation. It depends on a lot of factors. But what is interesting here is that they potentially have a unique signature, a footprint that allows us to identify them. For example, if you look at the figure 8 here, on the x-axis, you have the wavelength, which is the electromagnetic spectrum, where we are looking at when it comes to look to see the signature. And the reflectance is actually the amount of light that is being reflected by that object, the sunlight. And from there, you can see now that each of these objects on the legends have a specific signature. It can go from alfalfa, from corn, from grass and pasture. You can look at soybean, wheat, woods, and also stone steel towers. So each of them will be interesting. For example, when it comes to building a land use and land cover map, but also in terms of crop type classification. So these are the type of information that can be very relevant when it comes to agriculture. In agriculture, for AGWA, we are relying on 3 biogeophysical parameters that we are using as an input to the model, and a 4th one, which is the evapotranspiration. So here I'm showing similarly the signatures that we get from vegetation index. The first panel is located in Sarabiji in Kolda in the southern part of Senegal, and it is a cropland. And the second panel is the NDVI signatures in a location in Gao in Dakar, which is a urban area. What we can see here is that we can derive seasonalities and see actually how it is changing through time. And by using this information combined with the temperature, land surface temperature, by using the rainfall data and using the evapotranspiration, all of those 4 parameters will have an explainability power when it comes to modeling food crop production forecast using machine learning. Other secondary use cases are, for example, anomaly detection to see, for example, how the NDVI signal amplitude is changing. For example, looking at the seasonality shift, are we having a shift in the seasons depending, because of any change in the climate variability, but also to look at how short and the extent of crop growth stage. So for AGWA, we rely on vegetation index, rainfall, land surface temperature, and also evapotranspiration. Now, we just discussed about how satellite remote sensing can bring the wealth of data that they embed into the agricultural sector. But it means that also this is a considerable jump in terms of the type and the amount of data that we need to process when it comes to using those data for food crop production forecast. The figure number 10 you see here is a perfect example of a data cube. So basically each panel is going to be a different parameter, but you also have the depth of those of that parameter, which is time. So now we consider the latitude and the longitude as the coordinates, but also time becomes now a factor in terms of enriching the type of data we can use for modeling purposes. So remote sensing allows us to access massive and specific and detailed data, and the need to extract and exploit the amount of data cannot be actually done with traditional means. We need actually to use emerging technologies like machine learning with new architectures, with new ways of disentangling the data and finding the relationship among them. And that's what we did here after leveraging satellite remote sensing data. And then how do we now use machine learning techniques for that? Now we talked about the remote sensing part and data that we can use. We also, this is a graph that shows a simplistic way of explaining what most of the machine learning algorithms are doing. Actually, any model can be explained through this graph, where we have a training phase on your left and a prediction phase. So the training phase is where we teach the machine to understand the relationship between explanatory variables and response variable, basically your input X and your labels Y, or the parameter you are trying to predict. And the predictions is where now, after a training stage, you use your model in real life experiments and then try to have the outputs. On the training phase, the input X, in our case, for example, is where actually we have the remote sensing satellite data, such as vegetation index, rainfall, evapotranspiration, land surface temperature, and the label Y, in our case, is the historical production data. So what we do here is that we provide an input X, a scenario in terms of those biogeophysical parameters, and tell the machine that if you see this scenario, here is the corresponding production that we observed. And now the machine will do an internal cooking and try to adjust some parameters within the architecture and try to make a first guess, which is the prediction. And once we have the predictions, we compare what the model is saying with what we know from the input data and compare them. The whole goal is to reduce the residual until we reach a minimum difference between what the model is saying and what we know as the output. That is the training phase. And in there, what is specific to machine learning is in the gray box, where you will have different architectures, different aspects that you will have to take into account. For example, are you going to use an architecture that is more about artificial neural networks? Are you going to use ensemble method? Are you going to use, for example, time series analysis? And within those families also, there are a bunch of models that you will have to decide which one to use. For example, are you going to use deep neural networks? Are you going to use SVM? Are you going to use also XGBoost or decision trees? All of that are parameters or models that you have to decide which one to use. And again, within those models, once you have it, there's a fine-tuning aspects that also you need to look at until you converge to the optimal model. And from there now, we use the model that has learned the patterns and then go to the satellite, collect those biogeophysical parameters to make predictions. At the beginning of the season, we know that, for example, in Senegal, the rainy season is during the summer. We go and, for example, once we have the first rain, collect, for example, the vegetation index that we have, go to the satellite, collect your rainfall data, looking at also the land surface temperature and also the evapotranspiration, not only for the beginning of the season, but also for the last 20 years to drag all the historical pattern within the model. And then based on those trends, we ask the model, based on what you have learned in the past, what can you tell us in terms of production? And then the model will just do the predictions, and then we have the output. If you are interested into knowing more about the details about the model, the validation aspects, looking at the accuracy aspects, I encourage you to look at the publication that we published during the annual trend and outlook report in 2021, where you will have all of those details. Now, what to expect when you go to AGWA. If we stop just at the modeling stage, where we publish the paper with all the theoretical background, the equations, the validation purposes, the convergence, all of those field level expertise, it will remain among a few hands, and it will be very difficult to increase its outreach. That's why here, for example, remote sensing can help us to reduce the data, but it still, requires a lot of processing and cleaning and mapping expertise. Similarly, when it comes to machine learning, several aspects needs to be dealt with, and I just mentioned them earlier. Among them, you have the architecture, the model choice, the loss function, hyperparameters. Those can be far-reaching for the decision maker. Now, how can we bridge that gap between research outputs, but also how it can be used for decision making? That's where actually we decided to take the model output and embed it within the Africa Agriculture platform that is at a pixel level and also 24/7 availability, and that is cloud enabled. Now, in terms of AGWA conceptual framework, what we are doing here in a nutshell is that we move from raw data, satellite images, that might not provide any information because it's raw and just it will be like pixels with numbers. But it will require spectral band processing and cleaning, time series analysis, do sometimes some thematic mapping, prediction using machine learning, and all the analytics that will be preliminary to transforming the raw data into knowledge. And once we reach the knowledge, we need also to have some data-centric web applications aspects for accessibility, data visualization for interpretability, and the maintenance, which is very important for the sustainability. And we're very happy that for this sustainability, we have a team of machine learning engineers and data scientists and also web developers that are helping us actually to embed the model within the platform and to provide timely and accurate data on the platform to everybody. And then from the dissemination, which is where the decision makers and anyone who's interested in the data can take over for further analysis or for decision making. So if you look at this graph, there is a lot of field level expertise that is required to jump from the raw data to knowledge and the knowledge all the way to the dissemination. But the promise of Agua is actually decision makers and the end user in general doesn't have to deal with all of these aspects that are integrated within the Africa Agriculture Watch program and platform already. In terms of Agua main and upcoming products, today, when you go to Agua, you will have access to the community level crop production forecast, which is the main product of Agua. The second one is the potential agricultural land estimates. I think Dr. Usman mentioned that sometimes it's very difficult. How many countries actually, he asked a question, how many countries actually are having issues into knowing the potential agricultural land estimate, but the agricultural land, estimate only itself is complicated to have sometimes. We also provide ready-to-use vegetation index, the VIs, maps, and time series data. We not only provide the outputs of the model, we also provide inputs, the inputs that we are using to build the model, to provide insights, and also for the end user to see the trends and use it as an explainability tool to the forecast that we are providing. We also provide the ready-to-use land temperature maps and time series data. Most importantly, as well, we provide some briefs and bulletins, which is in the publication section, scientific publication, but also the briefs that we are providing for each production forecast that we are publishing on the platform, which is a fact sheet where the end user or the stakeholder, or the policymaker that doesn't have time actually to look at the platform and click on it and is more interested into looking at the facts. So we just provide that brief where you can look at the status or in terms of production and comparison with the previous year. We also provide biogeophysical data for the last 20 years. Now, currently, the team is working hard into uploading the greenhouse gases emissions measurement above croplands. Here we are starting with methane. You can see an example here on about the methane emissions above croplands in Senegal. The data is ready. It's being uploaded on the web platform, and you should expect in the next couple of days to see a new feature on Agua. We will be communicating around it, where you can access also to this information. Another tool that will be launched soon is the thematic fast mapping tool. This is a very important tool today. What we witnessed and realized by collaborating with country partners is that mapping is itself a very difficult aspect in the agencies. The softwares might be very expensive sometimes to have. The skills also, even if we collaborate in terms of capacity building and strengthening for thematic mapping, the turnover between agencies is very high. And the person that has been trained, for example, to do that mapping might not be in the same entity the next year. So we came up with the idea of building a portal, a platform, where you come with your Excel file or your data, and you go home with your map in just 8 clicks. So that will help actually to fast track and to increase the productivity and of creating maps. And the tools is ready. It's going to be launched soon, and it's going to be open access as well. And finally, a product that we've been working on for a while now is the crop type mapping. The work is advancing well, and we are hoping to have the first crop type maps soon about maize in African countries, but also other crops that are very important for rural communities as well. I think the best way to showcase what Agua can do and what Agua is about is to demonstrate. I am going to share my here the platform. So To access it, it's aagwa.org. You can see also the website here in the email. Once you get there, so far the platform is covering 47 countries and 9 crops. When you click on start, you will have this window. I will start with the menu, where you have the main platform where you can access the data. You have the about section where you have the narrative version of what AGWA is about, but also the team that is working behind it at Academia 2063, and the 3 pillars that we take into account when it comes to the Africa Agriculture Watch program. Forecast for decision-making, remote sensing data for African agriculture, and web-based tool for accessibility. There's a methodology as well, where we have also a narrative version of the methodology, but again, you can also look at the publication where you have more details when it comes to the methodology, and the publication section where you can see the briefs and also the scientific publications that we have. We've been working since COVID-19, as Dr. Usman said, where we have the bulletins and briefs. For example, maize production forecast in Northeast Africa, the case of Uganda, Kenya, and Ethiopia amidst the COVID-19 crisis. You can also look at the Ukraine crisis brief, for example, predicting food crop production in terms of crisis, the case of wheat in Zambia. And we can also look at other publications about remote sensing, machine learning, and other scientific publications. For the forecasts here also, we can have it in French and in English, where you have an introduction, some facts about the data, and a plain and simple table that shows by district and regions the production and the difference between the years. Now, let me go back to the main page where you have here 4 tabs. The 5th tabs will be about greenhouse gases above croplands that will be coming in the next couple of days. When you come to the pixel level forecast, you have here some drop-down lists about production and yield. We've been providing the data since 2020. Every year we are covering the entire continent, most of the countries. For example, here in 2023, we have predictions if we look at, for example, Cameroon and the crop for maize or sorghum. We can try maize and visualize the data. Once you get there, one feature that I would like to show is the interactivity. You can click any pixel and see the value in terms of metric tons that the AFCP model is predicting for this season. You can also have other visualization features in terms of changing the background map for, at your convenience. You can look at the word imagery or no base map at all. But also you can add the administrative level and click on them to know which administrative level it is. Now I am going to show the other visualization features in terms of pixel. Here I can just define the range of production values that I would like to visualize. Here we are visualizing between 0 and 1,279 metric tons in the country. And another one is also when you would like to change the color scale. Most importantly here, the data is available for download. You can have it as an image in a WYSIWYG format. What you see is what you get, which is a screenshot basically. You can also have it as a TIFF file if you want to do more analysis with the GIS software like ArcGIS or QuantumGIS or even Python when it comes to programming. And here the potential agricultural land that I was talking about earlier, where you can download it and also do more analysis. Now, I'm going to show as well the biogeophysical parameters. Here we have 3 of them: the normalized difference vegetation index as a proxy of greenness and health about vegetation, the land surface temperature 1 meter above ground, and the rainfall data from CHIRPS, which is the infrared group of climate hazard. If you click on, for example, Benue, you will have here on your right the panel where you have the data for several years, but also bounded with the maximum and minimum for the last 20 years for Benue. What you can do here is that first, the map is available for download as an image or as a PDF or JPEG. And this graph also is available for download as an image, but we can go full screen. And here what you see is that the green line is the minimum of the vegetation index in Benue for the last 20 years. The blue line is the maximum that has been observed in Benue for the last 20 years. And then in between, we put the values for the years that we covered so far, 2020, 2021, 2022, and 2023. What we can see is that if we remove 2020 and 2021, just observe 2023 and the mean value, we see that, for example, the value for 2023 is slightly above the mean value, but still in the normal range with regard to what we've been witnessing for the last 20 years. This information itself can help and maybe bring more explainability about the vegetation cover in the area. Now, when we go to the land surface temperature, we can try Benue as well. Here we can see also the same data and the same type of graphs and analytics that we have for the vegetation index. Here we have the maximum, the minimum, and what is in between. We can see that here the variation is higher a little bit, but still it is something that is following somehow the mean value for the last 20 years. Maybe we can observe, check for 2023, where, for example, until mid-January, it was above the mean value, but after mid-January, it started to be a little bit higher than the mean value. And we will be updating the graph as we go throughout the year. And then I will try to do the same for Benue. Yes. Here we have also the rainfall data. There also, here we can see the frequency is a bit higher because the data is daily compared to the other remote sensing data where, for example, it is every 16 or 8 days. Now we can look at, for example, 2023. Of course, we don't have yet the data because it's not the rainy season, but we can, for example, look at 2022 for last year and see how the data is compared to, for example, the mean value. For example, we can see clearly that last year, the rainfall was a bit higher in general than the mean value for the last 20 years, but it's not reaching the maximum value unless maybe here where we see that the maximum in 2022 was like closer to what we've been witnessing for the last 20 years. Now, this is like what we have for the biogeophysical parameters when it comes to the district level forecast. Here, what we try to do is that we have the pixel level forecast, which is interesting if we want to see more granularity and try to have maybe a more accurate or disaggregated history about what is going on the ground. But for a decision maker, it might be also interesting in terms of national planning to have the data at a subnational level, not all the way to the details when it comes to pixel level. And we aggregate the production forecasts by administrative level, either it is district or it is a county, depends on the country. And if we, here we have for Congo Republic and cassava, but you can always select the country that you want and the corresponding crop that you are covering there. For Iwo, for example, you can see that we have a production of nearly 30,000 metric tons. And if we look at for 2023, we also have 23,000. And now we compare the two and see that we have a percentage of change between the two. Now, what is interesting here is that we can have also a way of comparing last year predictions with this year prediction, and maybe for the stakeholder to take advantage of this information and start planning. And also we have the prediction calendar, but here it will become the map where we put the data compared to the data availability depending on the country. So all in all, this is the Africa Agriculture Watch as it is, and we will be adding more features and communicating around the new data sets that we will be releasing. You will expect to soon the greenhouse gases, methane above croplands, but also other parameters such as water availability profile, soil information when it comes to nutrient content, and other analysis that the team here in Academia 2063 and colleagues are producing based on the data. So I will be stopping here for now, and thank you for your attention. Back to you, Your Excellency.
Thank you so much. Thank you so much, Dr. Lee, for your very, very insightful presentation and keynote address that actually underscores what Dr. Usman alluded to in his welcoming remarks, that there is talent that exists in Africa in this space that will drive the future of agriculture, the future of health, the future of our economies. And you are one of the young, bright leaders in artificial intelligence and machine learning and remote testing and using data analytics to demystify what was hidden for most of the agriculture ecosystem and value chain. And your keynote address did convey the huge potential for our countries to leverage evidence-based data and embrace these emerging technologies, not only to enhance the productivity of agriculture, but to broaden agriculture and make it attractive for the emerging young, that with data, we can truly address the challenges that we have outlined. So thank you so much, Dr. Racine, and I'm sure that many in the audience and beyond will be interested in your presentation and to carry this dialogue further and to reach out to Academia 2063 to benefit from this new program being launched. So I thank you so much. Now we move to the promotional video that will introduce the Africa Agriculture Watch promotional video to all of us. If you can mount that, please.
Africa's food production systems are constantly battling numerous threats. From climate change and conflicts to health crisis, plant disease, and pest outbreaks, these shocks have in different ways brought to the fore gaps in the continent's crisis response capacities. The disruptions engendered by such crises require accurate and timely data generation to predict and inform agricultural production for better preparedness and intervention planning. However, data analytics with predictability capabilities are not readily accessible to decision makers across the continent. Academia 2063 is working to change this.
From the Comprehensive Africa Agriculture Development Program to the Regional Nutrition Strategy, or the recently adopted African Climate Change Strategy and Green Recovery Action Plan, wherever the African continent is going with these agendas, our role is to try and provide the data and the analytics that will help the member states define programs, implement them successfully to continue to make progress.
Africa Agriculture Watch, in short AGWA, is a flagship program where Academia 2063 is bringing on the table artificial intelligence for agricultural sector. So the main idea of AGWA is how can we know before the harvesting period in African countries what would be the most likely scenario in terms of agricultural production.
Established in 2021, the Africa Agriculture Watch web-based platform is contributing to the Agenda 2063 aspiration for a prosperous Africa based on inclusive growth, sustainable development, and modern and productive agriculture using science, technology, innovation, and indigenous knowledge. How? AGWA provides data to drive agricultural productivity by periodically releasing focus on food crop production for 9 crops across 47 African countries. This is achieved using its Africa Crop Production AFCP model.
Agua is based on two emerging technologies, remote sensing and machine learning. But the type of remote sensing we're relying on for Agua is the one from satellite images. So satellite images are pretty interesting because you can cover a large area with just a few pictures, but also you can have the same pictures several times in a year. That way you can do some monitoring activities. Machine learning is a set of architecture and models that are very good at predicting. So basically, how do you learn from historical patterns and then try to make a prediction of what would happen in the near future?
These predictions are embedded in ready-to-use Agua outputs and disseminated via agua.org, accessible through the following steps. Start. Select the year. Select the country. Select the crop. Click on Visualize and view the pixel-level map, clicking on each location to view the exact production value. And while you're at it, navigate to publications and check out Agua's crop production forecast briefs. But we don't stop here.
We would like Agua to be the place where African policymakers and decision makers will go to know what would be the most likely scenario in terms of agricultural production and crops.
We see ourselves as a mobilizer of African expertise to collaborate on data and analytics to support the African Union agenda and support African countries so that we all march at greater speed towards 2063.
Head to agua.org. Visualize, explore, download.
Thank you so much. I hope you enjoyed that video that we just have watched. We will now move to the next segment. Our next segment is a panel discussion. And I will be moderating this section, and I'm hoping that we have all the participants in place. Each panelist will get 4 to 5 minutes per question. I'm wondering whether Madam Madeline Diouf-Sarr is in the audience.
No, not yet.
Okay, so we will then move to Professor Martin Brandt. Is he in the audience?
I'm in the audience.
Yes, welcome, Martin. It's good to see you. We will go straight to the panel, but before we do that, can you take a minute to just introduce yourself once again, and then we can go straight to the questions.
Yes, my name is Martin Brandt from the University of Copenhagen. I'm currently located in China, so it's already night for me. We have a group in Copenhagen where we do a lot of work on satellite images, and we're using artificial intelligence. So we have close to 20 people, and everyone is using deep learning. So we're really going into the technical things. We have programmers, code, people who are very experienced with these things. And yeah, I will stop here.
Okay. Just to remind the audience that the theme of our engagement here today is leveraging artificial intelligence and satellite remote sensing data for decision-making in the African agricultural sector. So that is the context of this panel. And I wanted to engage Professor Brandt on a question, which is, what are some of the most promising applications of AI and satellite remote sensing data for decision-making? And the second part of the question is, how are these technologies already used in different industries and fields? For example, in your field.
Yes, my answer to this question is probably biased by my own work. I'm not working so much with crop forecasting and agricultural fields, but what we are doing is we are mapping trees, and I think for me the most important, or what is extremely promising in the field of artificial intelligence and remote sensing is to use the technology and images for object detection, so to find objects in the images, and this is what we are doing. So you would need images that have a relatively good resolution, where you need images, where you see objects, and then you use artificial intelligence to detect and map these objects. And for me, the most promising application on this is to map trees. This is what we are doing. Trees can also be related with agroforestry, with agriculture. They are an extremely important part of croplands. So the trees, they are everywhere in Africa, in croplands. And mapping these trees, this was always impossible. So we could never do these things because the satellite images, also as presented by Racine, they are just, resolution is not high enough. And now we have some revolutions in satellite images, and now we are able to see objects, and we can use AI to map the objects and the trees. And why would this so extremely important to do? Trees, they are extremely important for farmers. They provide a lot of ecosystem services, and they are carbon credits. There are carbon stocks, and if we are now able to map individual trees, then every smallholder farmer, everyone who owns only very little trees, they can be included in carbon credit programs. And this is then going towards the decision making, which where we really would like to be to have these technologies implemented, that we can use AI to map single trees over entire countries in Africa, attribute carbon stocks to single trees. So we have every year we can map every tree, every carbon stock of every tree, and then attribute values to these trees. Like if a farmer owns a few trees, then it's known what can they be included in carbon credits, and they can get compensated for keeping these trees in the fields. And that is it's not really yet operational, but these technologies, there are a lot of companies who are interested in investing in these things and setting up systems where smallholder farmers can be compensated for trees and for the carbon value of trees they have in their field. So even if it's just 2 or 3 trees, they can be mapped, and it can be repeated at an annual basis, and the farmer can be compensated if these trees are kept and not harvested. And our group in Denmark, we are working on making these things operational. So we want to do this, or we are already doing this at national scale. So we do this for countries, but also for continents if the data are available, and then also going beyond detecting species and finding more values of the trees, what values depend on species, trees can only be protected if we are able to monitor and to map them. And I hope my answer was not too far away from the topic of this workshop, but I think it can be put in the context of agroforestry.
No, thank you. You're on point, Professor Brandt. Thank you for that. And the second question I have for you is, what are some of the biggest challenges and limitations in leveraging artificial intelligence and satellite remote sensing data for decision making? And how can we address these issues to maximize the benefits of these technologies?
Yeah, I want to relate this to my first answer. It's what I just was elaborating is require satellite images which are normally commercial. So this is certainly a challenge, that high quality images are not freely available and are only commercially available. And there are initiatives right now like the NIC-FREE program, where the Norwegian government has spent millions of euro to buy satellite images that can be for Africa, that can be used. So that would be the solution, that funding organizations make commercial satellite images available. So the quality is relatively high and can then go beyond what is possible with non-commercial images. And then many technologies, they are relatively complicated to use. So it's all not really operational. These things, they are not really implemented in standard software. So it requires coding capacities. It requires specialists, computer specialists. And one possible solution for these things would be to partner more between universities and organizations that universities can also provide knowledge and know-how to for data processing and also providing computing power that would be needed for these kind of things. And then other things are that the estimation of carbon stocks is very challenging. Methods that are currently used have a very high uncertainty. So what we are doing is to map tree crowns, and then we convert the tree crown via allometry to carbon stock. But it's very uncertain, and new technologies need to be also developed. And again, I think that the collaboration with universities would be extremely beneficial to move beyond standard techniques. Thank you.
Thank you so much. Thank you for your valuable insight. And now I wish to take the opportunity to welcome our sister, Madame Madeleine Diouf Sarr, who just joined us a moment ago. You are more than welcome to this distinguished panel, and we appreciate your presence and making the time on a very, very busy schedule for you in Dakar. Madame Madeleine Diouf Sarr is the head of the Climate Change Division at the Ministry of Environment, Sustainable Development and Ecological Transitions in Senegal. Madame, you are welcome, and you may take a moment to introduce yourself, and then we get straight to the questions. The floor is yours.
Thank you, Professor, for inviting me to be part of a panelist on this brilliant panel forum on how to use satellite in order to support and assist country regarding the implementation of a different objective in line with the commitment under the Paris Agreement, but also in line with the implementation of the Climate Convention. Yes, I think I heard a lot of high element you have raised and the panelists have raised regarding the need for this technology in order really to help countries. I am talking about African countries, but also I am actually chairing the LDCs countries. So, for LDCs, the issue of data is really important. We know that we have data lack in a lot of LDCs countries, and I can say in all LDCs countries, and even in Africa. So the necessity really to improve the access to data, the necessity also to look at the level of accuracy of data. I think this is important. And in the process, we need to assess the impact of the different measures we're taking on adaptation, on mitigation, because someone was talking about carbon credit, about sink. And I think, yes, and for that, you need to have really some tools, some methodology to help countries to be in a position to assess. And I want just to highlight that if I look at the most sensitive tool, I think the issue is how to make it also accessible to the different institutions we have in our country. So the issue of training is important. I think we need to ensure that these tools became democratic, not something just for a small group of experts. So this to make it larger, widely usable by institution and also by universities and also students. I think this is important. And the issue of how to follow, how to monitor, as I already say, the impact of the response we providing. I think it's important. It will allow country to adjust when they are taking some measure. It will allow country really to improve what they are doing. As we know that adaptation is a dynamic, it's totally linked to the level of temperature the global world is facing. So how to assess this progress, I think is really important to use this satellite detection information, but help quickly to assess. Another point is, as I say,
Madeleine, before you go to the other points, I have two specific questions that I wanted you to address, and then you can wrap up with some of the other points that you wanted to make. Some of the points you have made actually did answer some of these questions. The first question that we have for you is, how can artificial intelligence and satellite sensing data be leveraged to support sustainable agricultural practices in Africa? And the second component of that is, what role can these technologies play in mitigating the environmental impacts of agriculture, such as soil erosion, deforestation, and water pollution? In your early submissions, you've actually touched on some of these, but we want you to come back to that and situate it around this question. And I have another question for you after that.
Thank you. So I will try to focus my statement around the two questions you have raised, as you mentioned it. Yes, regarding a satellite tool for agriculture, as I say, it will allow us to really first look at the situation, what it is, the status of the zone concerned. You know, we're talking about having a baseline. So I think it's important to have all this information in order to determine the baseline. So I think having an idea of a land cover at the beginning of activities or project or program, I think is important. And this will allow us to have, as I say, some data. And regarding the different adjustment you're gonna make or the measure you're gonna took, but you're gonna develop on the site or on the perimeter of a project, which will allow you to assess in a regular manner how the outcome of the project is going. So I think this is important. So this using this satellite instrument help to monitor, help to start, and help to look at the progress, and also to check whenever you have some problem, how to raise this problem and find some solution. So as I say, it's really important. And what I'm saying is also, yes, you need also to make it accessible. So this is important for us. Who is the owner of this information? How to allow communities, because we're talking about communities, we're talking about also national institutions, how to ensure that they have this information, they have this capacity also to use this data from satellite and make also the assessment that it is required. So I think this is really clear. Your second question is, I think, is linked to the deforestation, the mitigation part. As I say, if you
as well, and water pollution.
Yeah, and water. Yes. If I look at the issue, I think the point is, this is a tool that allow really countries to monitor what they are doing. If I look at the case of deforestation, we can have more element, I think, in a quick manner on the rate of deforestation. We can also check the driver of this deforestation. In particular, if I'm talking about the production of biomass energy. So we can have an idea of how a site is being aggressed by the different driver of deforestation, and from there have some solution. So it's an opportunity for that. Regarding the water, I think also regarding water is clear. If you know, we have a surface, and this surface is supposed to, if we look at our arid zone, we know that we're gonna have high temperature. It's increasing, so the evaporation will be more and more high. So the surface of water zone might be more and more decreasing. So how to follow that? I think it will be good really for service in charge of hydrology to have such kind of tool that in order really to check the impact of high temperature or whatever also parameter like wind erosion or wind erosion or rain erosion. We can check that. But the issue for me is also it will give us regarding water, how to manage, how to organize the harvest of water, and maybe help to define some management, what we call sustainable management of water due to the variation, due to the climate impact. So yes, this tool is really important, and my call is really to ensure capacity is there for institutions at the local level, and they are in a position and accessible, because we always have to talk about cost. It's important. So and we need to do things urgently. So these are aspects I think we need to take on consideration. Thank you.
Thank you, Madeleine. The last question I have for you is around examples. If you may, can you provide examples of how AI and satellite remote sensing data have been used to promote biodiversity and ecological resilience in the African agricultural sector? And what are some of the challenges that need to be addressed to ensure that these technologies are used in an environmentally responsible way? You have talked about some of these challenges and some examples of how to address them, but if you can engage us further.
Let's give some example. Yeah, great. Regarding, we have done something with FAO, and I'm in a meeting where we have many, many stakeholders through around some project going around the LDCF, is the fund related to least developed countries and on adaptation. And there is what we call the example of Champ École. It's a process to build the capacity at rural area to use good practice regarding some technology to really have some rational use of water and in arid zone. So the satellite allow us, and allow because it was the first assessment done by CSE and Senegal National Meteorology and ASIM. So they have covered through this satellite information, but different what you call it, but different most exposed zone due to water limit, water scarcity, and from where we start implementing some strategy. And I think what come up from this experience is there are some tools, there are some technology that can help really communities, that can help farmers to still have a sustained productivities by using this technology. I just take the case of Zai. It's a technology, but some other country like Burkina use it, but in Senegal we have difficulties to use it because some barrier or cultural barrier. So this is a solution. You go to the field and you saw that this is a solution because it's respond to the limit of water availabilities, and it allow and guarantee that farmers will have at least some production some production for the household. So this is important. So having this kind of experience being replicated everywhere, I think it will be a good opportunity to show to the world that this solution or solution applicable in arid zone is something that we can promote widely in arid zone. So this is and it is kind of the satellite can be a way to check all that and monitor how it's working. Thank you.
Thank you so much, Madam Madeleine Diouf Sarr, for your very insightful intervention. We're very much grateful and appreciative. Now I move quickly to Dr. Racine Lee. And Dr. Lee, you may want to begin by briefly commenting on what you've heard from the panelists. But more importantly, I have two questions for you as you do that. The first question is, how can artificial intelligence and satellite remote sensing data be used to help small-scale farmers in Africa to improve their agricultural productivity and livelihood? And the second question for you is, what are some of the challenges to implementing AI and satellite remote sensing data for decision-making in the African agricultural sector? And how can these challenges be addressed? Are there any policy or infrastructure changes that would need to be made to enable widespread adoption of these technologies? Some of these you have touched on during your keynote address, and some of the panelists have also touched on this. So you can perhaps add to those interventions. But first, you can start with your immediate comments on the very insightful exchanges with the panelists. You have the floor.
Yes, thank you, Your Excellency. I would like to first thank Martin and Madeleine indeed for first their time, but also the insightful information and also application and examples that they provided. I think when it comes to what I've heard from the panelists, I heard about the application of remote sensing and machine learning when it comes to tree covers and using high spatial resolution satellite data. And this is a perfect example of how machine learning and applied and combined with satellite remote sensing can go to beyond the agricultural sector. Everything is interconnected actually, because there are some studies that are showing also that crop might play a role of carbon sinks. And I think we have one presentation later on that will be touched a little bit on it. And I think the application is actually helping us to assess and to apply these technologies to improve decision-making as well in other sectors like, for example, carbon market as well. And from Madeleine also, I heard about very important aspects. For example, the capacity to for the capacity strengthening activities. How do we make sure that the satellite remote sensing data availability is increased across the agencies and also the stakeholders? We're very happy that actually at academia also, and more importantly for with the Africa Agriculture Watch, everything is downloadable, and then the data is made available for download and further analysis. The whole purpose actually is not only to provide forecasts in food crop production, but also how do we make sure that the whole process of collecting the satellite remote sensing data, the processing, the quality assurance, taking out the unreliable pixels, and all of those technicalities are not going to be on the side of the end user, but on the side of the data and analytics providers, such as Academia 2063. That's actually, we are very happy that we are contributing to disseminating remote sensing data to our colleagues. And also, I really enjoyed the stock taking exercise that she mentioned also as well for the baselining when it comes to land cover, but also for crop mapping in this case when it comes to the agricultural sector, where, for example, how do we disentangle myth from facts? For example, a good question we asked, we said like 60% of arable lands in Africa are not being used. Actually, remote sensing can completely help and make sure that we have the exact or at least close to the exact number with that, given how dynamic the land use is evolving. And also the fact that there is a real opportunity, a real potential when it comes to identifying changes and how do we attribute those changes and identify the drivers of deforestation, but also in terms of crop rotations. Here in this case, for example, we can, when you have a crop type classification or a crop type map, by running the classifier several times, you'll be able to see how crop are rotating. So I think all of those are showing the full potential of remote sensing and machine learning when it comes to the agricultural sector and beyond. And this is very, very important to emphasize. Now, when it comes to the question, Your Excellency, how can AI and satellite remote sensing data be used to help small-scale farmers and also to improve the agricultural productivity and livelihoods? I would like to try to answer this question by being a bit futuristic. Even though what I'm about to say might happen very soon, but at least it has the benefit of putting us in a space where each of us will see a different potential. I'm not going to talk about, for example, the accurate predictions small-scale farmers would get from AI-driven analytics. Rather, I will focus on other aspects. For example, the main help from satellite remote sensing, I think Martin talked about it, is this, that can be beneficial to small-scale farmers, are an increased disaggregation and all the way to their farm size, which means the use of high-resolution multispectral satellite images. And the multispectral is bringing more explainability. But the AI side, one advantage that I would like to talk about is for small-scale farmers to benefit from the AI connectivity and updatability capabilities. Let me explain myself. Very quickly, if we take if we use the example of a human doctor and an AI doctor, it has been shown that for some tasks, the AI doctor is more accurate than the human doctor. And usually the comparison is, by the way, unfair to the human doctor. In reality, when you hear an AI doctor, you should understand a family of AI algorithms that are sharing information and learning patterns to improve themselves, while the human counterpart is a single doctor. The good comparison would be between a group of human and AI doctors. That's one thing. But the time it would take for a new vaccine, diagnosis, or medical discovery to spread among practitioners is still significant, while for the AI, it is a matter of an update. And that is the result of the AI connectivity and updatability. But on the contrary, one might say that a wrong diagnosis as well, or drug significant damage. But a second is also possible with the AI doctor. I want a second opinion from the Microsoft AI doctor. I can check with the Google AI doctor what would say. And a patient with such a tool might actually benefit from a better healthcare service than the wealthy person that can afford the best specialist. Now, when I bring all of that into the agricultural sector and especially for the small scale farmer, similarly, a farmer can identify the pest or disease in her or his field with a picture captured from a smartphone and have a bunch of proposals to solve the issue coming from several AI agronomists, and she might have a better service than the wealthy farmer that can afford the best specialist. And that will bring now preparedness, efficiency, and subsequently an improved livelihood. So that's, I think, that where actually the trend is going when it comes to small scale farmers benefiting from that. Now, for the second question, and I will try to be brief on this one, the challenges to implement AI and satellite remote sensing data for decision-making in the African agriculture sector, and how can these challenges be addressed? There are two things that I can think about when it comes to AI and remote sensing in Africa. First is the labor. It is very hard to find machine learning engineers with extensive experience or understanding with the equations and the details of the complexity of those formulations, since it is a fairly nascent field in Africa. The second is that the availability of data. Sometimes the data can be available, but not accessible. Those are two different concepts. Agencies that hold the data are sometimes reluctant to share the data. And I think it's like it can be attributed to the lack of maybe understanding about the use that maybe the machine learning practitioners intend to do about it. But their progress is being made really. But for the second question, policy or infrastructure changes to enable widespread adoption, we can consider a two-level approach. The first one is like the usual drivers of a good ecosystem that can facilitate data collection and sharing with, for example, big open data platforms where data is available, and just to make sure that we are feeding the community to be innovative. We need also like good internet speed, because when it comes to, for example, updating those AI agronomists in rural communities, we will need actually to have that internet speed for updating those models, for example. An increased computational power that is accessible to practitioners, for example, big computers or computer centers that are available in the country, and to practitioners and universities, and make it easy to access. And also to have national AI policies to sort of regulate the sector. And like currently in AI in Africa, the approach is a bottom-up approach. And how can we also have a national plan to produce AI champions for the national labor, but also how to exploit the already existing talent. And my last point is that those are changes that will help you to hit the ground running within the current global AI trend and competition. This is very good. But I think the biggest change, Your Excellency, we also need to consider for a wider and proactive, therefore sustainable adoption, is to consider technology also as a national strategic sector similar to agriculture, finance, and security. One of the reasons why those sectors are important is that if they suffer from failure, people's livelihood will be seriously impacted. The change that AI is bringing on the table is similarly profound, and humans moved from physical to cognitive labor during the Industrial Revolution. But AI now is competing with us on the cognitive side. Where else will humans shift to? What are the consequences in terms of, for example, market labor, livelihoods? I think those are the second level questions we need to also answer, not for only the purpose of bringing changes, but for the purpose also to build a responsible and tailored strategy to adapt to that change. Those are the two levels of thinking that I wanted to share here with the audience. Thank you. Back to you.
Thank you, Dr. Lee. Thank you. Very profound interventions. I thank you most sincerely and thank all the panelists. But before we go to break, I wanted to turn quickly to our many participants across the world. We have some thoughts and questions on the chat that I wanted panelists to take note and maybe have a minute intervention each, if possible. The first was one from Kenneth Yakubu. In his chat, he says, leveraging AI will increase the visibility of Africa's food production capability to stakeholders within and outside of the continent. And his question is, how will access to this data be governed in a way that ensures African countries are self-sufficient and are competitive in the global food market? Another question that was raised in the chat is, would the AGWA platform also capture data comparing predicted and actual crop yield and production over a time period? And I think, Dr. Lee, you may want to shed light on that. Another intervention or question is from Nyabyenda Jean-Paul from Rwanda. He says that this is an interesting open platform as far as agricultural data availability is concerned. And then he asks, is there any way you can develop tutorials for self-learning and utilization in different teaching universities and colleges across Africa? What strategies are in place to make sure that a number of policymaking agencies and research institutions are exploiting this platform for more evidence-based policies and accurate data? I think, Dr. Lee, you can touch on that. Another one is from Eric Maniragua. He says, what types of satellite data are best suited for yield prediction and why? We have a last one, which is on Microsoft. It says, Microsoft wants data-driven agriculture to be democratized. Microsoft wants the benefits of data and AI to reach every farmer anywhere in the world. What are the opportunities and challenges? And then he queried, what about data ownership? These are just few questions that came across from a diversity of participants. If you can quickly take a minute to respond. I called upon Racine for the specific questions, and then the others, we can have Professor Brandt and our sister, Madam Sarr, to take the floor. Dr. Racine.
Yes, thank you so much. For the first question that I would like to address is would AGWA compare predictions and real data? Indeed, this is an exercise that we do within the team by comparing what AGWA is predicting with the historical trend, just to first check if this is a first level check to make sure that the predictions are not far from what we've been witnessing and collecting in terms of production. But at the same time, there is also what we call out of the bag comparison, just to assess the accuracy of the model. When we will look at what the model is predicting and what we have in terms of observation and compare the data. So far, what we have is a very close relationship. The correlation, I mean, if you do the ratio between what AGWA is predicting and what the data is saying, we have something very close to 1. And for more information, I really propose to colleagues to look at the publication. There you will have all the details country by country in terms of accuracy. And we also ourselves make sure that the data or the briefs that we are publishing are very coherent with what we could expect from countries. And we're also discussing with colleagues in countries to make sure that the data are not very divergent from what we've been witnessing. And when it comes to tutorials, capacity building in universities, and so we do have some capacity building strengthening activities that we do in countries. And for example, when we do the eAtlas, which is another platform under the RESACS program, where we do there, for example, geospatial mapping capacity building activities, and we intend to go all the way to artificial intelligence, more specifically machine learning. And I think also there's another core program, the AgroDep, that is intended to open an AgroDepo AI school where we will be also training and working with experts in AI. Now, in the use of the platform by decision makers, I think a good proxy to showcase how AGWA is keeping up the momentum into being a key tool for decision makers to have access to those data and predictions is the request for having a customized AGWA. So some countries now are interested into having the same platform, but customized with the country crop diversity and also intervention planning. And we are working on that. And also we know that some colleagues in countries are a good user of the data, and we'll be sharing that soon enough once we have the first AGWA report in terms of outreach as well. For data ownership, this is a very tricky one because the way we build the model, it is based on remote sensing data, which is an open access data. We use open access data. Sentinel-1 and 2 are openly, freely available. MODIS is freely available. So therefore, the type of data we collected to build the AOCAP is not tied or linked with personal data. So we are trying to respect actually what we call the digital public goods principles and the responsible AI, where no one can come and link the data with a human being. And that's also a way of ensuring that we do no harm when it comes to providing those predictions. And now, I think by having these receptacles to discuss with decision making and having high-level panels with decision makers, we also help to bring together all the stakeholders like researchers, policymakers, decision makers, to increase the awareness of how AI and machine learning can help. And we will be having similar events very soon. Thank you, Prof. Over.
Thank you so much, Professor Brandt and Madam Sarr. Any reflections on the questions raised in the chat? Professor Brandt, if you can take a minute. I don't seem to see Professor Brandt. Is Madam Madeline online? If you can just quickly share some reflections.
She's here, but she might have stepped away.
Okay, so I think Professor Brandt has also stepped away, but I think Dr. Lee had touched on the essence of those questions. So I want to take this opportunity to thank all of our panelists for a very insightful and very rich contribution and exchanges this morning. So now we will take a 10 minutes coffee break, and then we will resume.
Prof, sorry, yes? Prof, 5 minutes.
After 5 minutes, I will do a virtual coffee, so I will be fine. So we'll take 5 minutes. So when shall we come back?
We come back at exactly 12 noon GMT.
Okay, 12 noon GMT, and those that are in my time zone in Geneva at 2 o'clock.
Wherever you are, just at the top of the hour.
At the top of the hour, yes, wherever you are.
Yes.
I will join you with my virtual.
All right. Thank you, sir.
Thank you so much.
Yes, Prof, we're back and the background looks good.
So everybody is back?
Yes, we are here.
Okay. So good afternoon, everyone. Welcome back. We are now moving to our next segment, framing remarks, the AI trends in remote sensing, agriculture, and climate action. I welcome you all back to this session and part 2 of our engagement today, this afternoon. I will now invite Mr. Zi Gao, the Senior GIS Coordinator at the International Food Policy Research Institute, IFPRI, to share remarks on AI trends in remote sensing. Mr. Gao, you have the floor.
Hello. Can you hear me okay?
Yes, we can hear you. You can have
Okay.
adjust your camera a little bit so that we can see your
yeah.
face fully. Thank you so much. And you can introduce yourself quickly before you get to your intervention.
Yeah, let me
Okay.
share my screen also. Okay. Can you see my slides at the full screen? Hello?
Yes, hello?
Yes,
You
can
can.
share your slides. Yes.
Okay, can see my, okay, great. So my name is Zhe Guo, and I'm from International Food Policy Research Institute and based in Washington, DC. And we are a consortium group on international agricultural research. We have 14 centers and around the world. And this is just give you an overview. And so even though IFPRI is the only center based in Washington, DC, but we have over half of the colleagues are based in different country offices. So my topic is AI trend for remote sensing. I'm a geographer by training, and so I will just kick off. So a little bit background. So we all know, like in Europe and in US, there's quite a lot of advanced application for remote sensing for mapping.
Sorry, Mr. Guo, we cannot see your slides. Are you sharing?
Yes.
We cannot see your slides. No.
How about now?
No, we don't. Are you using the arrow at the bottom of your screen? Yes, now you have started sharing.
Oh, okay.
Okay.
Great.
If you go to reading, perfect. Wonderful.
Great. Let me move my this thing. Great. Sorry for the problems. And so yeah, I'm from IFPRI based in Washington, DC, and we have under the consortium group of the International Agricultural Research. We have 14 centers around the world, and our center is based in Washington, DC, but we have over half the employees overseas, majorly in Africa and Southeast Asia and South Asia. So I want to have a little bit background for the remote sensing, very short. And so we all know, like in US, in Europe, and the example on the right, and the University of Maryland have developed very successfully, like the USDA's from US, the CDL, crop data layers. They are operationally used, so with accuracy over 90% for crop type mapping over many years, starting from 1997 up to now. So they generate data every year. And the European Research Agency also similarly generate crop type mapping, not just a cropland, but also crop type mapping using the Sentinel data, as Dr. Lee mentioned. And also the forest heights, not just forest coverage, and also canopy heights, and land cover and cropland dynamics over time series. Those are a few very successfully and well-known applications around the world. But and then in recent decades, I think, especially in the last decade after the launch of the Sentinel data and the time series of the Landsat data, both provide very high resolution images, public available. But so researchers can step into the contents of Africa. But still, I want to highlight a few challenges. I mean, for Africa, one is the spatial heterogeneities. So the land, not unlike the US or the Europe, the land is highly disaggregated. So the average size in Africa, the cropland probably 2 hectares, and then also very complex farming practices. So within the same plot, you can have half of them are maize and half of them are different crops, and also intercropping. All of these issues happen very small parcels. So we have to keep that in mind when I borrow the method or we learn from the method has been developed in the US and Europe. But I think the rapid revolution of remote sensing technologies is provide promising solutions now. Majorly, I think I want to emphasize on these 5 points. First thing is the public available data at high resolutions. So not just the high resolutions at spatial level, which is 10 meters from Sentinel and 30 meters from Landsat, which can capture the small scale heterogeneities, but also the temporal resolutions are largely improved from 60 days to 5 days. And this is very important for agriculture because the growing season usually lasts for 3 months. So we need revisit time. And the last another point, additional point is the spectral information with the fine-tuned, the satellite equipment, so they can capture the agricultural part or the vegetation part very, very closely. The second point is the cloud computing. So it used to be a bottleneck, like we have to have better, very expensive machines to run these algorithms. Now the cloud computing, especially Google Earth Engine introduced by Google, it's almost free. I think it's very fast, and then most of the data already in the back end of the server on the cloud. So there's not too much cost to acquire the data and to process data, to prepare the data. And also the third point is the machine learning packages. Most of the packages like the R-based or Python-based or even the cloud-based, it's very low cost and or no cost. So we make it suitable to implement to the different regions, different areas. And also the fourth point is the processing time. So nowadays the satellite data can almost available in real time or in close to real time, like with the lag time of a few weeks, 2 weeks, 3 weeks, and the satellite data available for everybody. And the last point is the ground truthing point. I put the underline of that because that's the key of the machine learning. I think that's one of the areas, although the Africa has, like Dr. Lee mentioned in the slide, there's a lot of data already collecting, but the quality and the quantity is still not comparable to the, like, for example, the CDL from the Europe. I think that's the part we need to improve that to get the ground truthing data, which is the key drivers of the machine learning algorithms. We are improving in Africa, but
Hello. It seems that you're frozen. Can anybody hear me?
I can hear you, Prof. It seems we lost.
Yeah, I think his screen is frozen. Can somebody get hold of him?
Okay, let's try a few seconds. He dropped off. I think he's trying to reconnect. So perhaps we give him a couple of seconds and see if he makes it.
Okay, let's just give him a few minutes. Yeah. Shall we move to Dr. Shah, and then he can join us again later?
Yes, we can do that.
Yes. I want to take the opportunity to welcome Dr. Parmesh Shah, Global Lead for Rural Livelihood and Agricultural Jobs at the World Bank. Dr. Shah, you're welcome. You can quickly introduce yourself, and we look forward to your remarks on AI trends in agriculture. Dr. Shah, you have the floor.
Thanks a lot, Your Excellency, and it's a pleasure to join this group. And I want to congratulate Dr. Usman and Dr. Lee and academia for really harboring a new data revolution, which is completely owned by Africans, run by Africans. And I think it augurs so well for what could happen in future in Africa. And it's indigenous, homegrown, and really it shows that so much talent exists within Africa. And we have to harness it and use this platform to take it big. Warm congratulations to the whole academia team for really making this happen. I would touch upon some of the work we are doing in World Bank, and then also link up with how we can collaborate with academia and what are the trends we are seeing in the work on AI, use of AI in agriculture globally. I am right now in Korea, and we are currently looking at how Ministry of Agriculture in Korea is using data, AI, machine learning to really develop a new architecture for extension advisory to farmers using all these functionalities. In the World Bank, in the last 5 years, we have invested in data as a public good in many agriculture operations. We have currently 53 operations going on globally, of which 14 and 15 are in Africa, which have invested in, I would say, a data platform and innovation platform, and then use of digital technologies and digitally enabled extension services in many countries. And I think and the work done by academia will also give us a very good foundation to really build the content of new kind of policy making and new kind of implementation, which we will be able to do in various investments in Africa. So, what is the investment which is required in data is that there is a lot of investment in data centers and all. People keep on accessing data, and our analytics is that 80% time is spent on collecting data, only 15% time on analysis, and 5% on utilizing the data through use cases. So I think this particular work which academia is doing can invert this ratio completely. Because what you are doing is that you are making data accessible, you are providing very high quality analytics, and then making people use this data more and spend more time on using data, as opposed to analyze and doing that all the other things, which I think require a good level of expertise. And we are, at a very suboptimal level if we don't change this ratio there. What I like about thing is that crop yields can be predicted through AI even before a vegetation cycle is started, because that is not based on the current crop situation. It's based on the land use, the soil, the moisture, and you can make crop prediction before the actual crop is even planted. And I think this data to have can really help in many ways. It can help in the financial. We know that only 7% smallholders in Africa have access to formal credit. So we are trying to work right now on a credit score for smallholders in Africa, which would be based on the kind of crop prediction data which academia is trying to do. If we had good quality data, something like USDA's data, which is always available, using satellite data and, historical data, ML and all the techniques. And so if we could create a credit score for smallholders using this data, that will allow us to really do a very, very wonderful kind of new investment in agriculture, which will lead to productivity increase and also access to markets. The second thing is that there is a risk perception about what is smallholder growing and how much have they produced. And I think if we have data on that, then a lot of services can be built better. Currently, if you look at amount being spent on fertilizer subsidies in Africa, we make a lot of investments in fertilizer, but we are not sure whether that fertilizer is first really required for that type of land, and second, whether it is having an impact. So currently we are working on a crop optimization, a fertilizer optimizer tool, and we found that 38% of soils in Kenya have turned acidic because of excessive use of phosphorus. And if you give more subsidy for phosphorus, that will become even more acidic. So you will have problems on, quality of soil and lots of other things which we are talking about. So I think if we want to reverse that, if we had a way by where we look at soil fertility, we look at optimizing what the soil quality is, and then we look at the crop protection, and we bring all this data together and come out with the recommendations on customized precision agriculture, fertilization for smallholders, we will be able to, through combination of AI and ML, be able to do that. Currently, we have many innovators in Africa who are using sensors. And this is what I would like to say. I think use of sensors at the ground is very critical to be combined with the satellite data and others. So what is happening in now many countries that they are collecting the data through sensors of soil moisture and also soil fertility. And that data is converted into actionable analytics by comparing it with millions of soil samples which already exist in the globe. So you are using the advantage of all the soil samples which exist in the research system, combining them with the individual observation you have on a farm, and you are coming with much more precise recommendation of soil fertility from that. So AI is able to do that because you are able to get the sensor data, the historical data, and all the soil fertility data which you are getting from satellite all talk to each other. Because if this data does not talk to each other, you don't bring rigor in your recommendations for a farmer. So I think that is a very big breakthrough which can come in through the kind of data which is being collected through the kind of web-based platform which Dr. Lee described very ably. And if we bring the IoT, the AI and all those things together, it will become a very functional kind of tool. And I think in Kenya, we have built a million farmer platform where we have 38 startups using this data. So we have invested in a big data platform with Ministry of Agriculture with KALRO. It has registered all the farmers digitally. It has geotagged all the farmers. and it's also digitized all its research data at one place, and all the farmer organization data is also digitized. This data is available to researchers, available to the innovators which are developing products and services. And I think if we are able to do the crop prediction, then the insurance, the credit market will completely be, will be a very different market. And with the digital platform we have on payment services in Africa, in many countries, if we combine that with this prediction analytics, then I think we are able to come up with a much better formulation there. The second point, which has been made by other panelists also, will be the whole area of soil carbon, which is going to become very important in future. And we are now trying to develop a carbon credit market, voluntary and otherwise, for smallholders so that they can get carbon credits, not only for trees, but also for the conservation practices they are adopting. So if you adopt conservation practices and you are able to demonstrate increase in soil carbon content, then you will be able to really get credit for that, and a new flow of income for an African smallholder farmer for carbon credit can also be developed there. Finally, I think the World Bank is investing in combining our digital investments in infrastructure, which is what Racine also talked about, the internet connectivity, the digital ecosystem. So we want the digital projects of the World Bank and the agriculture projects to be invested together, where agriculture projects work on making all the digital investments work for smallholders, and the digital project works on building the digital infrastructure and connectivity and the ecosystem, which makes it favorable for agriculture innovations to take place. So I'll stop there and once again congratulate the Academia team, and we look forward to collaborating with them in many countries where we have made investments. Thank you, His Excellency, over to you.
Thank you so much, Dr. Shah, and thank you for your very insightful contribution, and particularly recognizing this trailblazing leadership that Academia 2063 is leading, and your readiness to collaborate and partner with them to reinvigorate these very important activities led by African talent. We have now our colleague, Mr. Zi Gao, whom we lost due to technical difficulties back. We are going to give him back the floor to continue with his intervention. Mr. Gao, you have the floor.
Hi, do you know when I drop off? Do I drop off at the very beginning of the slides, or?
I think you can just go back and quickly, to refresh people's mind from the beginning of your presentation, quickly go through that and then proceed. You are at the middle of your presentation.
Okay. Can you see my slides?
We can. Yes, we can.
Okay. Okay. So I would do it. What's going on? I would do it very quickly. So my name is Zhe Guo. I'm from International Food Policy Research Institute, and we are a global, centers, and one of the centers under the CGIAR, and we are based in Washington, D.C., and but we have over half the colleagues are based in Africa and Southeast Asia and South Asia. So I want to begin my slides with the achievements. We have a well-known products developed from the US and European space agencies. And from the right three examples, basically you can see the USDA and from US developed the crop data layers at 30 meters annually from 90s to now. And the accuracy is very high. It's over 90% of the crop type mapping and 99% accuracy for crop extent mappings. And also the European Space Agency also can map crop type maps different crop types or the major crop types in the continent. And Universal Marine Alliance is leading the mapping of the forest, at very high resolutions, and also not just the land cover where forests, where the cropland, but also the cropland change over time. Because the improvements of the satellite data now can improve very high resolutions and the time series observations over space. But I want to highlight 2 points, which is quite key for when we move the technology of remote sensing. We have the success stories to the contents of Africa. One thing is the spatial heterogeneities, I think, in Africa, which the land of the smallholder farmings are very small, and compared to Europe and the US, it's around 2 hectares per household, and in average, and make it extremely difficult to apply directly using the algorithm or method from the US or the other countries. The other thing is the complexity of the farming practice. I think it's also like the farming practice in Africa is much more complicated as we see or implement different studies in the past, intercropping and subplot, they have different crop types within the same plots. Half of them are using for maize, half of them are using for like totally different crops, and then maybe some of them are partially irrigated and the other is not. So it's very, very challenging. My next slide is gonna say, okay, right now is actually the right time to implement the remote sensing to Africa because the rapid evolution of the remote sensing technology, which lies in these 4 perspectives. So one thing, as I mentioned, is the spatial resolution has been much more improved from 250 meters MODIS data to now Landsat 30 meters and Sentinel is 10 meters. But not only just the spatial resolution, but also the temporal resolution. So the release time is now like almost like weekly. You can have weekly observations if not daily, and which is it's key for agriculture monitoring because agriculture we need shorter gaps in observations to monitor the crop changes and crop growth or the dynamic of the vegetation changes. And the last point is spectral information. I think it's spectral because of technology, the spectral resolution of the satellites also largely improved, so we can more accurately reflect the changes of the vegetations of the crop from the space. The second point I want to say is the computing platforms. It used to be quite expensive. You need to high-end performance machines to handle, to prepare, to process the satellite data. Now, the cloud computing platform like Google Earth Engine is totally free, and most data we are using actually from the satellites, they are already archived there and in almost real time. And the third one is the algorithms. So from machine learning, different machine learnings, support vector machine, and all sort of applications, and to deep learnings. Most of the packages are available for free or very low cost to implement for the data analysis to generate the crop type maps or the productions or yield through this sophisticated analysis of remote sensing data together with other data sets. The fourth point is the data, because we are always keen to, for agriculture, want to get the close to real time or near real time observations and monitoring. Now the lag time to release the satellite data is within weeks. So within 1 week, 2 weeks, you get the data for free already. And the last point, which is I put the underline there, is the ground truthing data. I think that's the key of the machine learning applications for agriculture, especially for Africa. I think that I see the ground truthing data are largely available and the quality also improved quite a lot, but still they are not comparable to what they have in the US and Europe, and in terms of the quality and the amount of the ground truthing. I think this is a part we need to make efforts on to further take advantage of the improvements of the technology of remote sensing. We need more ground truthing and also make them public available or or available in some ways, so we can train different models to improve the accuracy of applications. I want to flash a few applications like of the remote sensing done by the different universities and agencies. One of them is like yield estimation led by Stanford University. They already makes effort, try to use the high resolution images to map the variation of the yield across space. And also the crop type mapping led by, or the forest mapping led by the University of Maryland. Now they are also implement in the contents of Africa and Asia also. So all of these, and also of course the Harvest Plus program is a large program, 50 million program. So the agencies, the NASA is investing big money for apply the Earth data to informing agricultural decisions. And there's a lot of interest in this, and has been involved very actively in different studies. And also the private sectors also step into these crop type mapping, and not just crop type mapping, but also by system, like is it irrigated or is rain-fed, something like that at different scales. So promising results has been generated. And for us, I'm working on the spatial data analytics theme. Our team has been testing or different applications, apply different applications for crop type mapping in the contents of Africa. So like we test how sensitive to the ground truthing data in South Africa, and also how we collect the crop cut yield and try to estimate the yield for within seasons to see how accurate the remote sensing data can provide the yield estimation across space. But we need to think a little bit more, because we have these technologies. We have, I think they are highly applicable in Africa now, because the spatial resolution has been largely improved. But we also, I think, to be practically used, we are not just want to know where the croplands are. And furthermore, we want to know where are the arable land, where are the permanent land. And in addition to that, I think the hierarchy, like to make it more useful, we want to further separate that to rain-fed, irrigated, and when is the growing season, when it start, when it's end, and more importantly, it's a cropping patterns. Like, and also we are not only interested in the area, and also it's the yield. So all of this information together with the remote sensing, I think then we can provide more meaningful information for the policymakers or for the decision makings. So we are thinking for that, like in another word, we want the whole application, remote sensing application, to be operational, not just for research. Okay, we prove this is doable, but also operational, how it works as a system. Like Dr. Lee mentioned, like we can inform the forecast of the predicts of yield productions by collecting the ground truthing data and in the front end, and drive the model to give all of these estimates at different scales and to see different purpose. So for that, I want to just put a few words for the model has been developed by our institute. It's a spatial production allocation model. So they use the modeling approach together with the remote sensing data. And right now we put more weight with the remote sensing data because the improvements, as I mentioned. The reason we're still using modeling approach, because I think at current status, the remote sensing is still not stable or not capable to map many crops. We are all interested, because for a country, we probably have more than 10 or 20 crops. For this model, we originally developed at the global scale. So we try to map 42 plus. Now we have, in the 2020, we're going to map 46 crops across the world. And the model now adjusts to not just for global studies, but also for regional and country studies. So we bring down the spatial resolution from 10 kilometer to 1 kilometer, and but for country studies. And also in the temporal, we right now by design, for global, we want to do every 5 years to capture the changes of the production and the yield and area in the 5-year gaps. But now we are try to generating the annual products, at least for the country studies. The output of the SPAM it's not, like I said, because the researchers or the policymakers, decision makers, not just onto the area, but also the production yield and value of production. So we generate all of these products by system, which is irrigated and rain-fed. We split further into a high input like commercial farming, or low input like without much fertilizer or irrigation interventions, or system farmings, where are these crops distributed across space at a final resolution for country studies, but at a little bit coarser resolution for global studies. And the maps on the right, upper right, is an example for regional studies at 1 kilometer, and we can bring in more details when we zoom into the country studies. But for global studies, we keep it at a coarser resolution. The more information can be get at the website list at the bottom. And this is my last slide. And I just want to emphasize remote sensing is not just for agriculture, but also for monitoring different things, like the drought monitoring has been very successful applications of remote sensing globally and or in the contents of Africa. And also during the COVID, we use remote sensing to monitoring the NO2 concentrations and also the nightlight differences across time, and to see how the human activity on the ground. So there's a lot of promising, in summary, it's a lot of promising studies coming out because the improved of the remote sensing technology. I think this is the right time to apply that in the Africa, because of the improvement of spatial resolution, temporal resolution, and also the spectral resolutions. I will stop right here, and for any questions, I'm more than welcome. But thank you again for the invitation.
Thank you so much. Thank you, Mr. Goh, for bearing with us and coming back to share your very valuable insights on the AI trends and your work in this area. Now I call upon Dr. Muhammadu Bambasila of AIMS Canada, who is the AIMS Canada Research Chair in Climate Change Science in Rwanda. Dr. Sila, we look forward to your intervention, and you're more than welcome. You can quickly introduce yourself and before you go into your contribution. You have the floor.
Thank you very much, His Excellencies. I'm Muhammadu Bambasila, based at AIMS Rwanda, expertise in climate modeling and climate change assessment. Let me share my screen very fast. So I'll be going to present a little bit about AI trends in climate actions. So I'll try to use as much as possible this outline where I set the scene from small introductions, show how AI can improve climate models, talk about mitigations in the sense of carbon sequestrations of agriculture, and discuss a little bit about natural resource management and how AI can help about it, and end up by a short summary. So this is a generic slide where we all know that in Africa we have a high climate risk, and this risk is increasing with global warming. And when it comes to climate change, in Africa, human lives and economic countries are at stake. So we have to take strong climate actions, effective adaptation and disaster risk reduction. So climate action is just action needed to, let's say, reduce greenhouse gas emissions and increase resilience and adaptations. And AI can help about that. Let's start by the climate modeling side. So climate modeling is developing climate models, as I used to say, and climate model is just a tool to simulate the response of the climate system, the global climate system, to a certain forcing. It's a representation of the three-dimensional, numerical representation of the three-dimensional fundamental equations that govern the functioning of the atmosphere, coupled with land surface model, ice model, ocean models, and cryosphere models, those kind of things. So we have a schematic of climate models like in this plot with the discretizations. And if we want to actually improve climate model's output, we have to push into 3 axes. The first axis is the resolution, where we go from, let's say, 50 kilometers to 10 kilometers, 5 kilometers, increasing the resolution. We think you result more processes, and then you're having better simulations, or increase the complexity, adding more and more processes to the model, or just increase the ensemble size. Increasing the ensemble size means you actually perturb the initial conditions or something in the model, use the same version, perturb it a little bit, and have one member, perturb again, have another member, and you can iterate this for a long time. So this is the ensemble size of a model. So luckily, or let's say strangely, so multimodal ensemble is actually working better in improving climate models output. And this is the workflow when it comes to climate modeling, where we use observations to actually develop models, where there's equations, parameterizations, and all of that, the numerical resolution and all of that. And then we use that model to actually do simulation. When we're doing simulation, we actually prescribe to the model boundary condition or boundary forcings from observation again. And then when we have the results, we test the validity of the model with observation before using it for any development of climate information and projections, analysis of the results. So there is a lot of potential for application of machine learning here from the beginning till the end. For example, if you mind the color observations, here we can apply machine learning for climate data monitoring, quality control of data fusion from different sources, but because most of the time the data comes from different sources. So when it comes to the model development, you can emulate model components, develop improved parameterizations, because something that I forget to say is the climate model has 2 components. You have the dynamical core that the model can resolve, the variable that the model can resolve, and then you have the parameterization, the physics, where we use empirical relationship. So this comes from, this applied to radiation, cloud microphysics, precipitation, and other things like, let's say, turbulences in the boundary layer. So then we can have improved parameterization of the physics. So when it comes to the simulation itself, where we have to provide boundary forcing, let's say you're running a regional climate model, so it can help, like machine learning can help to have better suited boundary forcings, like by correcting, going beyond the traditional bias correction, by correcting your boundary forcings and inputting in the model. And then also using, let's say, nudging it for physical consistency between the driving model and the RCMs itself. So when it comes to the results now, we can see that here bias correction can be key if you're going for some impact applications. Features detection, we'll see multimodal ensembling, because better multimodal ensemble, you're having better results, better projections, and then better regional climate information to feed into your climate services or into your impact models or into all those adaptation intervention. So you can also uncertainty quantification or also further downscaling. The example of this is multimodal ensembling, where Jose et al. Used 2 versions of CMAP6. One of them is the next GDDP datasets, and then probably the normal CMAP6 is interpretation, minimum temperature and maximum temperature. And we can see that the correlation and the root mean squared error is always better when using the different machine learning models than the simple arithmetic mean, which is the mean here. So this also appears when you look at the scatter plots. We have the simple mean, arithmetic mean, and the different machine learning, where you see the coefficient of determination is always high when you use machine learning techniques. So you have better multimodal ensembling, you have better information for the future, better predictions, better projections. But it has also been used for further downscaling. what happens is we have GCMs. We usually downscale GCM using RCMs, that is physical dynamical downscaling. So 11 RCMs have been downscaling the GCMs here. And then another machine learning, deep learning model has been built to actually downscale the GCMs by training a CNN and having a model emulator applied to the different GCMs here. So we have the precipitation in the red and the temperature in the left in red. So we look at this, and then down we have the bias. So when we look at this, we can see that the bias is much lower, and using the deep learning technique to actually downscale the GCM. And this is great because lower bias, better projections, and like I say, better information for the future for different sectors, better adaptations, and so on. It can also be used to do some attribution. So usually attribution is just when you actually, the process by which we evaluate the contribution of different causal factors to a change. Yeah. So we have a change and then we see what are causing it, and we have different possible causes, and then we look at the different causes and say these are the causes. So that is the attribution process. So usually we use climate models to do the attributions, and it's just in a very simple way. We have the observed changes, and here the observed change you want to attribute is increasing warming in black. So we run our models with only natural factors, and then we run the models with human and natural factors. And then we can see much of the time that this warming is attributed to human activity. So that's one of the conclusions we can get from this graph. So now deep learning comes into play as well. And let's say disentangle the different factors like natural factors, aerosols from anthropogenic, greenhouse gases from anthropogenic activities, and it even goes beyond that and give attributions for specific years where some things happen, like volcanic activities or El Nino, that is a wave of warming. All right. Now we look at mitigations in terms of carbon sequestration, like I said, for agriculture. So first of all, we have to keep in mind, and we all know that agriculture is a source of emissions, like carbon dioxide emissions. So from the beginning to the end, like from the cropping to the processing, transport, electricity used for irrigation as well, for different source of emissions. But it can also be a carbon sink, and that's the good news. So how? Because we have crop photosynthesis. When crop is doing the photosynthesis, they uptake carbon dioxide, like the carbon from the atmosphere, and use it with some light and other things. Use it to actually generate what they call in bracket their food, which is kind of energy, and releasing oxygen. Okay. So, but this carbon dioxide that was uptaken will be stored in the soil actually. So, and as long as the soil is cool, no problem. But any disturbance to that soil will release the carbon to the atmosphere, and then that will increase carbon dioxide in the atmosphere, more warming, more greenhouse gas, more greenhouse effect, more warming. So, which means we want this carbon to actually stay in the soil, right? So then you have different agricultural practices that can, you have the blue one, which is residual removal, excessive tillage, and other things that can release this carbon to the atmosphere, and then causing, of course, decline in soil and environmental quality. And then you have this one in blue, where you have residual retention, so they say cover cropping or catch crops, some practices, and minimum tillage, which is very important. You also have agroforestry or livestock integration that will help to keep the carbon into the soil. So then we can see many applications of machine learning techniques here. So first of all, in the monitoring and measuring. So AI can help here to actually identify areas of large was combined to remote sensing, like satellite imagery. So that can help to actually identify area of large emissions, polar emissions. Okay, and identify what other policy or practices that are causing this. So that's one thing, which is very important. So monitoring and measurement, and then we have the reduction. So we can have to reduce. So because it can be used to actually do some soil analysis. So because if you have soil analysis, you can see whether you're going to have a less application of fertilizers, or will release carbon dioxide, double release greenhouse gas in general, or less water requirement as well. So we can also have, can be used also for crop selections, like is this crop require lesser use of water or more use of water, and those kind of things. So I enjoy identifying the best practices to reduce the emissions. It can also be used for the removal of greenhouse gas, because it can detect areas of woody plants. You have these woody plants encroachment, which means some of the woody plants are growing in some areas. So we can identify suitable conditions for this, why this is happening, and then speed up some kind of reforestation, like undertaking agroforestry. So we know the suitable conditions. Let's undertake agroforestry. So these are key issues on how agriculture can help sequestrating more carbon. We also look at how AI can help for natural resource management. So this is these are 3 examples of natural resource management. We have forestry, we have preserving and restoring wetlands, and we also have protecting and restoring ecosystems, marine ecosystem or coastal ecosystems. So if you take the example of the forest, so what we want to do is manage the forest, improving its management, reducing its degradation, right? So the first thing that we will need to do is, of course, mapping, like doing inventory, like having accurate forest data. All right, so having satellite imagery and AI can help to actually do this inventory, mapping the different species, which is very important, seeing the tree grows, and then have the potential for sequestration, so carbon sequestration. And then once this is happening, then we can find vulnerable forest area where AI can help track illegal mining, roads, fires, housing. These are activities that can favor deforestation. It can also help to stop illegal logging, like track. You have different sensors in the forest, of course, and these sensors, and you develop AI to actually connect to this, and then let's say track the noises, listen to the forest, and track the noises of chainsaw or logging trucks. So this also can help to stop the illegal logging, which is also a source of in Africa. We also have reforestation. So reforestation is key, but speedy reforestation, because otherwise it can take time, and then the effect can be in the long term. If you have speedy reforestation, where you can monitor, for example, the tree growth, you know where the woody plants are coming, popping up. All right, so you know the optimal conditions for this, and then you can know what kind of species you can select for the reforestation in one area or the other area. So which is also helping for the speedy reforestation. So this is the summary of how AI can help to, in general, combat climate change. So we have the mitigation in blue, and the adaptation and resilience. We didn't talk about it, but it's still there. It can help a lot of working on adaptation and resilience. And then we have the fundamental science, like climate modeling, climate research, and other things, right? And it's all about data, okay? So data complete and process data, satellite, fill some gaps in time and space, strengthen planning and decision making. This is key, and optimize processes. So that's how we can use AI for different mitigation and adaptation resilience. And then also some of the fundamental items that like climate finance, like forecasting carbon prices and those kind of things. So I think I've come to the end of the presentation, which was very short. That's remarks for climate action using AI. Thank you so much.
Thank you. Thank you so much, Dr. Sylla, for your very insightful presentation. we're very appreciative and thank you. Now I will invite Dr. Rasin Lee to come back to us for his reaction to the framing remarks on artificial intelligence trends in remote sensing. Dr. Lee, you have the floor. You can come back to us. Thank you so much.
Thank you so much, Your Excellency. I'm going to talk about a little bit about my friend Goze's presentation, and indeed a very deep explanation about the trends of AI in remote sensing, and actually from a practitioner, which is very interesting to me. And he raised all the challenges that we are facing when it comes to applying remote sensing and machine learning in African agricultural landscape. And he rightfully said that remote sensing and AI in general are not only for the agricultural sector, but there are some other possibilities into applying them. But I just would like to emphasize a few points he raised. For example, the farming practice complexity in Africa. For someone who would like, for example, to build a crop type mapping, you will need to take that into account. We are well aware of that within the team. And also from discussions we're having with colleagues such as Goze, where actually the intercropping and the mixed cropping practice on the ground is making it difficult to extract a unique footprint of crops in Africa. And that's one of the biggest challenges when it comes to build a crop map and all the subsequent applications that you can have with that output. But also the fact that we have a small crop size, which means also to have to use the high resolution or moderate resolution satellite images. One of them that is very mostly used is like Sentinel, which is 10 by 10 meters. Above that resolution, there might be commercial satellite data. And also, I do agree with the fact that it is the right time to implement remote sensing and to Africa because of the temporal and spatial resolution. One point that he raised also is the data quality and quantity. It is very nice and important to develop those tools, and we see also the advantage it can bring when it comes to decision making, to do some stock taking exercise, baselining. But we should not forget, as he said, that those tools will require extensive and quality data to build those models. Even building a crop type map requires actually to have quality data and also massive data. So an investment that will be a preliminary work towards implementing remote sensing and machine learning in Africa is to invest into collecting quality data. Things are being done in countries. Now we just need to ensure that that data will be accessible to practitioners and then feedback the process of decision-making in countries. And also he talked about the need to collaborate, the spam snapshot data. I'm saying snapshot data because it is even spam is very critical to what we are doing. Some data are coming from different sources, and our added value is into bringing predictions on the table into the process of decision making. And we need to see how we can fulfill the promise of remote sensing in Africa. There are initiatives that are happening also within the continent. I know that the African Union also space agency is being implemented and is expected to be also a good driver when it comes to collecting and having a framework where remote sensing can be implemented within countries at the high level. But when it comes to projects at Academia 2060, for example, we have the DERPIN project, where we are implementing such methodologies and technologies in 5 countries in Africa. And the first part of that project is to collect ground truth labels when it comes to crop type. I really appreciate his intervention and look forward also for collaboration and also to hear from other colleagues. Thank you so much, Your Excellency. Over to you.
Okay, thank you so much. Thank you so much, Dr. Lee. Oh, can you hear me? Can you hear me?
Yes.
Audible. Okay, thank you so much for your remarks and for your reaction to this. Now we'll move to another distinguished colleague, Dr. David Laborde Diboket, who is the Director of Agri-Food Economic Division at FAO, to share his thoughts for the framing remarks on AI trends in agriculture. Dr. Laborde Diboket, you have the floor.
Thank you, Professor Ka, and first, thanks for Academia 2063 to organize this event and to have invited me. And I would say thanks even more for bringing this great platform and this great tool to the community. And I will say in my remarks a few words about what this community look like. But I also want, obviously, to thank Dr. Shah for his presentation. I think it was excellent. So I will just give me maybe a few perspectives on and some key points that I think should be kept in mind of how to deal with this question of AI in agriculture, knowing that clearly it's a major disruption in most economic sectors, including in agriculture. I also want to quote what Usman said at the beginning, that both in the communication revolution, we have seen how Africa can leapfrog some stage of development in some sectors. And today, beyond leapfrogging, actually Africa can also lead some of this innovation in this domain. Now, when we think about AI in agriculture, I will even say we should think about AI in the whole agri-food system, actually from farm to fork. Today, you will see AI used to improve tracking of nutrition, improve advice about what is in diet, so from the up to the plates. And of course, starting with what we are discussing today about improving the primary production. But I just want really to point this food system relevance and along the value chain, and in some cases, even in terms of optimizing logistics, big investment of AI play an important role in terms of tracking and sustainability, where AI combined with some blockchain technology can really change things. Now, on what's happening on the farm, I think that on one hand, we see the information system like the African Agricultural Watch today present us allowed to make better decisions, because I think that that's key. Why you want this, and Racine was presenting it at the beginning of in his keynote speech. Why we are doing all of this is to make sure to make better decision by policymakers, better decision by business people, but also better decision by farmers. And that's something we really want to keep in mind. It's going to increase productivity. It's going to increase profitability when it has been used, but also it's increased sustainability. I think that thinking about today precision agriculture without AI, for instance, will be a major mistake, and in some places not even possible, to track and to process large amount of information in order to make sure that we deploy the right response at the right place and at a high level of resolution, that you need AI to support what humans are doing. And just to be clear, AI is not here to replace humans. It's just to improve human productivity, human capacity to make better decision, better action, and at the end, for farmers and smallholder, that should translate in higher income. Of course, I will come back to some question about property rights. But just to say that it's a reality in terms of precision agriculture. What you also see, for instance, is the use of AI in horticulture, for instance, contribute to reducing food waste and loss, both by helping to better harvest and pick at the right time specific fruits or vegetables, and linked to what I was saying, post-farm, optimizing the logistics, reduce time of transportation and cost of transportation, and at the end, also avoid that we lose a product. So in terms of profitability, that's already occurring. In terms of sustainability, also it's important. Now, and to go back to one of the points I was raising, we want to make sure that Africa is leading, and in particular that smallholders are not excluded from this revolution, either due to a lack of connectivity, because even if today we see that we have a very large degree of connection with cell phone, that's going to be a mistake to think that everyone is connected at high speed in the world, including in Africa. We also have to think about inclusivity in terms of gender, to make sure that women farmers have access to both the hardware and the software, because unfortunately, we have seen in the past that other technology have not been inclusive, including about who benefit from it from within the household. So we basically don't want to create a new digital fracture. And if we see still today, how on the farm AI is used in high-income countries, from greenhouse in the Netherlands to the large soybean field in the US, up to optimizing urban farming in Singapore. Let's be honest, today, Africa, even if they can have access to the technology, doesn't have the financial means to deploy it and deploy it at scale. So we also, innovation is good, but we now want to make sure that it's not going to increase productivity gap, because what the world needs is actually to close some of the productivity gap. The last point I want to make is about data. So using AI also require to have good data to start with, but also to collect more and more data. So on one hand, for example, if you think about a lot of the AI that are done to optimize the application of fertilizer or optimal irrigation, you still need to make sure that you have good soil map information. And that's something in Africa that we still miss to some extent. Some can be solved by remote sensing, but at one point you also need boots on the ground and resources to do it. And that's something that at FAO we are investing and we are supporting countries in this work. But also all the data collected, I think it's here we have also to be very careful about the property rights of this data. Big companies, of course, know that a lot of the value of what they will do in AI is about selling services, and the value of services depend on the data we collect, and sometimes we try to own. And also we need to make sure that farmers, big and small, but in particular the small, doesn't lose what belongs to them, and doesn't have to pay a few years after for services they are ready to create. And here we need to have the right governance framework, but also legal framework. And let's be honest, across the various countries in Africa, we have some countries that are very advanced in their legal system and some that are just lagging behind, as we have seen a few years ago, for example, with biotechnology. And we don't want to create, a frontier where there is no laws and where you bring technologies, or where you will see companies doing things in Africa that they are not allowed to do in Europe, for instance. And so that's where, developing the policy framework, and also, and I will conclude by praising also Academia 2063 for the work they do, beyond this type of tool to help farmers, to help other economic agents along the value chain and helping the academics. It's important to explain to policymakers what are the challenges at stake. Because a lot of this technology may be sometimes, a bit mysterious when they are not mysterious. And we need also to make sure that we have the right governance and policy framework to use them, to deploy them, but also to avoid major new market failures coming from them. Thanks a lot.
Hello, can you hear me?
Yes, we can hear you now.
Okay, thank you so much. Thank you, Dr. Labor. Thank you for your intervention. And now we move to our last discussion. Professor Benjamin Lamte, a visiting scientist at the West Africa Science Service Center on Climate Change and Adapted Land Use, WASCAL, to react to the framing remarks on AI trends in climate action. Professor Lamte, we look forward to your intervention. You have the floor.
Okay, thank you very much. Can I share my screen, please?
Yes, please go ahead.
Can you see my slide?
It's loading. Yes, now it's on.
Okay. Thank you very much, and thank you for the opportunity to be part of this important workshop. I hopefully will complement what my friend Bamba already said, because we are in the same areas in terms of work. So by way of introduction, I'm at the WASCAL Center headquarters now, but I used to be the Acting Director General of the African Center of Meteorological Applications for Development in Niamey, Niger, before I went to the University of Leeds as a Cheney Fellow. Okay, now to the subject matter. I have a question. What comes to mind when you hear climate action? And Bamba mentioned it earlier on. And I want to make a point here because normally I take it from the Sustainable Development Goal number 13. Normally, when we talk about climate action, we focus a lot on climate change. And I want to make a point that there is an aspect of the climate action which is not only climate change. We need to look at the other time scales. And that comes from the same SWG number 13. If you go down to the targets, the goals are there, and then below the goals, we have the targets. And Bamba mentioned the word, he said resilience, that's 13.1. Strengthen resilience and adaptive capacity to climate-related hazards. Resilience goes beyond just climate mitigation and adaptation. And then the third one, improved education, awareness raising, human and institutional capacity on climate change mitigation, adaptation, and then impact reduction and early warning. Impact reduction goes beyond climate change information. Need emergency information and operational information as well. And the early warning must be coupled with early action. Now, the issue about resilience is that it's a bit different from adaptation. Resilience has a dual function. It has the ability to absorb the shock as well as self-healing, whilst adaptation adapts or absorbs the changes that have already occurred or may be projected to occur in the future. So resilience, the climate action story goes beyond mitigation and adaptation in this sense. And another thing I want to bring out is everybody is interested in climate change, and therefore we are aware of adaptation, but something that we normally overlook is the coping strategy, which has to do with the variability. When a farmer wants to know whether the rains start early or late this season, that's not climate change. That's operational information, and that helps him in his planning as well, whether the rainy season will be good or bad, whether there will be a long growing period or something. These challenges are there, and these farmers are coping with these things all the time. And the coping strategies that these people are using can actually help us in the adaptation measures which come out of climate change. So basically, they are saying that, note that the projected climate change events which we talk about, when they actually occur, they occur as weather events. Now, so it is very important to build weather infrastructure in anticipation of climate change. Bamba spoke a lot about climate changes. He expressed where AI can be used in terms of mitigation and even modeling. So basically, I'm making the argument that we need to also consider other timescales, because resilience is effort across all timescales, from nowcasting to synoptic forecasting, sub-seasonal forecasting, seasonal forecasting to climate change timescales. That's about resilience. And along these lines, in fact, the Google AI team are already using AI outside of the climate change timescale. They are using it for flood forecasting. And I want to show, and one of the challenges where AI will be very useful is producing forecasts at a community scale, which is something which is challenging using the conventional methods, very high resolution for decision making scale. And this Google team is already doing something like that. I want to show a video from what they are doing.
Hello, Prof. Are you muted?
Are you hearing it?
Okay, we can hear. We can't hear any sound coming.
Oh, you can't hear the video. Oh. But can you see the video?
Yeah, yes, we can. We can see the video, but no sound.
But you can't hear. What do I do?
Check whether the sound button on your screen is off.
Oh, okay.
On the presentation slide.
Yeah, it's on.
Prof, yes, we can see, but we cannot hear. Since we are pressed for time, perhaps we can just continue with the slides.
Okay, yeah. Let me. Okay, so basically, I would rather call these issues more than just challenges, issues that we need to consider in terms of weather and climate modeling or weather prediction. Weather generates a lot of data, and this data comes from different sources, different parameters, but the machine learning systems rely on consistent input data. Secondly, we can use machine learning in the understanding and modeling of the interactions in the Earth system. The Earth system has components. Recap what Bamba about. It has components. The atmosphere, the ocean, all these are in the model. And the interaction among them, most of the time, the science, basic science is understood, but the interaction is a bit challenging. And there is not enough data in terms of the climate regime, so machine learning can help in this area. Secondly, the world is round, as opposed to the neat images and tables of classic machine learning programs. So to build this collaboration, we actually need domain scientists to collaborate with the machine learning experts, and we can have customized solutions with physics-informed machine learning systems. The other thing is that the climate models use programming languages like Fortran because it's fast, but we are all aware that the machine learning models use Python. There's an issue to get these two words to communicate in order to solve problems. And we must also be sure that the machine learning systems are not just for climate change, but they are also they are operational forecasting systems, which is real-time synoptic weather forecast, and also robust climate change changing regimes. These issues are more or less opportunities for machine learning because some of them are already being addressed in terms of machine learning. So why do we have to use it? And that's what I have there. Thank you very much.
Hello, can you hear me now?
Yeah, I can hear you.
Yes, we can hear you.
Okay, thank you so much, Prof. We'll now go to the next segment, which is our general discussions we are pressed for time, so we will take few questions for the next 5 minutes. If you have any questions, you can raise your hand and then we'll give you the floor. There's one hand raised, but I can't see it. So
yes, Prof, it's there's a hand from Laulai Ibrahim.
Laulai, you can please proceed. Can you unmute and ask your question, please? Laulai, you have the floor. You are muted.
Hello.
Mute. Yes, you can unmute. Hello, you are still muted. If you can unmute yourself. If you can hear us, can you please unmute yourself? Now he's completely gone. Do we have any other questions on the floor as he tries to come back to join us with his question? If you're having challenges, you can also type your question on the chat. I will be happy to read it. We don't seem to have him back. So any other questions?
Oh no, there are no questions in the Q&A.
It seems there is no questions and there's none on the chat either. So I want to take the opportunity to thank the panelists and the valuable interventions that have been made. And I wanted to tell Prof. Benjamin Lumpty that I have something in common, which is WASCAL. When I was the Vice Chancellor of the University of the Gambia, I spearheaded the WASCAL program and hosted it in the University of the Gambia, and it continues to really make a huge contribution. So I appreciate your intervention and your work on the WASCAL program. We will now invite Dr. Ismail Ilofi, the Chief Scientist at FAO, to deliver the closing remarks. Dr. Ismail, you have the floor.
Thank you very much, Professor Mohamedou. Good really to join you and glad really to be part of this interesting event on AI. It has been quite enlightening to listen for the last hour or so to the insightful update about the Africa Agriculture Watch initiative and its strong potential for supporting decision-making for the transformation of agri-food system in Africa and the achievement of the Global Development Agenda. I would like really warmly to congratulate the leadership of Academia 2063 and all partners for this excellent initiative. The need for such a program cannot be overstated. Various statistics tell how data and its analysis has become contemporarily extremely important for Africa and the world. It is right now estimated that in every second, we have about 1.7 megabytes of data that is generated by every person on the internet. These data are about the crop we produce, the food we eat, the diseases that erupted, the policies that we design. And it is very vital that Africa fully embraces digital technologies, artificial intelligence, satellite, drones, and other emerging technologies to leverage proactive data insight. It's a time in history where there is an opportunity for us to leapfrog with the use of all these technologies in Africa. FAO has developed the Science and Innovation Strategy, which was endorsed last year by the Council in June. The goal of our strategy on science and innovation It's really that the FAO members, including the African members, harness science and innovation to realize context-specific and systemic solutions so that we can have a more efficient, more inclusive, more resilient, and more sustainable agri-food system to reach our four betters: a better production, a better nutrition, better environment, and better life, leaving no one behind, as part and parcel of our delivery on the 2030 development agenda. We all know how FAO has been supporting countries since its inception on effective agri-food data management. In 2020, FAO launched a geospatial platform in the framework of its hand-in-hand initiative to support countries to implement better targeted agri-food intervention. This platform uses advanced modeling and analytics to identify the biggest opportunities to raise the income and reduce the inequities and vulnerabilities of rural communities who constitute the vast majority of the world's poor. It contains over 2 million data layers covering food production, food waste, climate adaptation and risk, value chain development, policy implementation, and other themes. They come from different FAO databases, including FAO stat data, as well as key international institutional databases. We are very glad that we have more than 30 countries in Africa that are involved in the hand-in-hand initiative, and many of them are using and contributing to this geospatial platform. I can see great opportunities and synergies between both the Africa Agriculture Watch portal and the hand-in-hand geospatial platform. Moving on to the other subject that is very crucial, and I'm very happy that it is at the heart of this discussion, artificial intelligence in agriculture is expected to grow at an annual rate of 23% between 2023 and 2028. FAO has embedded its promotion in many of its digital activities in Africa. For example, in Senegal, in the framework of Digital Villages Initiative, FAO collaborated with Polby, a Senegalese company which offers satellite and AI-based services to advise farmers on nutrient needs of their farms and provide yield forecasting to the farmers. In South Africa, in Zambia and other countries, FAO promoted Plant Village, a solution that uses machine learning and AI and artificial intelligence to provide farmers affected by fall armyworm with tools for diagnostic and management of the fall armyworm. FAO is also collaborating with a company that will leverage AI to enable the availability of affordable clean energy for rural and agricultural communities in Rwanda. And these are just a couple of examples. There are much more, and all of them are on our website. Other related innovative initiatives that we are supporting are our data lab for statistical innovation that uses cutting-edge methods to provide granular and targeted information for countries. And of course, the WAPOR, which is the Water Productivity Open Access Portal that uses remote sensing technologies to monitor and report on agriculture water productivity. Building on our various innovative data analytic tools, FAO has been able to guide countries and the United Nations on food security and climate emergencies, including the provision of a close to real-time information on food prices since the outburst of the war in Ukraine, and also to support the COVID-19 recovery interventions. Dear colleague, as we have seen, the possibilities of digital technology seems endless, and new innovations such as the famous AI tool, ChatGPT, which will also revolutionize agriculture advisory and activities, are emerging constantly. We need to better understand them. We need to understand their benefit, but also their limits and how to address any risk that they may pose. I'm connected today from Boston, and yesterday I had discussion with the colleagues from Tufts University on how ChatGPT is changing the life of professors at the university. and how it makes it so difficult to make sure that really the student did the work, or have they used ChatGPT? And my approach was that if that's happening, maybe we should revise the way we are teaching. So we can't stop the technology. We have to take advantage of it. We have to use it. So if there is an issue, so we rather put it as the basis and then see how we change the way we are teaching the student at the university and make sure we give them the skills that they need. Whatever can be done by technology, and it's well done by technology like ChatGPT, maybe it's not needed in the next few years. We will pass that role to the learning machine, and maybe we have better things to do and use the brains of those students and of human beings in this planet. To then take fully advantage of digitalization, it is imperative that we improve the digital readiness of African countries and of the agriculture sector, the institution, including agricultural research organization. And that's really one of the requests we hear again and again from many of our members from the G77 plus China, whereby really we need to strengthen the local agricultural research organization. And we need to make sure we provide them and we work with them very closely to make sure that they are operational and they are really following the latest scientific development and innovation development. So according to the International Telecommunication Union, ITU, in 2022, only 40% of populations on the continent has access to internet, with only 23% in rural areas. And there are strong disparities among countries. Only 34% of women benefit from this connectivity. In addition, while the use of mobile phone is now widespread, poor infrastructure and the high cost of mobile data are persistent bottleneck that agricultural organization and rural community face daily. And again, here we need really to make sure that the private sector comes on board and really balance it out. But of course, private sector alone cannot do it. We need really to make sure that we have the right policies, the right regulation, the right incentives to have a competitive market for telecommunication and for connectivity in Africa to make sure that the prices come down and the service quality gets up. We need to better address these challenges if we really want the agriculture sector to be more productive, more resilient, and more fulfilling to all stakeholders, particularly to the small-scale producers and the youth. So as stated by our Director General, FAO is committed to digital agriculture transformation and the use of innovation to end hunger and improve lives and livelihood of ag-based communities. We are ready to take on our part of the challenge, and we look forward to collaborating with you to collectively achieve a world free of poverty and full of opportunities for all. Thank you very much for the opportunity to talk to you today. And really, for me, Academia 2063 is the strategic partner, and seeing you taking the lead and bringing partners around the subject, like really digitalization and AI, it's very important. And seeing the Africa Agriculture Watch really being launched and being working and serving the community, it's a big plus. Thank you very much, and over to you.
Thank you so much, Dr. Ilofe, for your illuminating closing remarks. We thank you with appreciation. Now I will invite Ms. Wanamba, Ms. Leah Wanamba, who is representing Mr. Hassan Nyambe. Ms. Lee Wanamba is the Senior Policy Officer, Climate Change and Desertification Control at the African Union Commission. You have the floor, ma'am. We look forward to your remarks on behalf of Dr. Nyambe.
So, Executive Director for Academia, Dr. Usman. I'm going to read this statement on behalf of our Director, Hassan Nyambe, who is in a parallel session and not able to join us today. Distinguished delegates, ladies and gentlemen, all protocols due observed. So I would like first to thank Academia 2063 for inviting us, the Commission, to this event, which is the launch of the Africa Agriculture Watch, AAGWA, under the theme of leveraging artificial intelligence and satellite remote sensing data for decision making in the African agriculture sector. I'm just going to check if you can hear me.
Yes, we can.
Okay, thank you. So the event today is important to us as the AUC, as it relates to the African Union's Agenda 2063, the AU Digital Transformation Strategy for Africa 2020 to 2030, the AU Climate Change and Resilient Development Strategy and Action Plan for 2022 to 2032, and the AU Green Recovery Action Plan, which is running from 2021 to 2027. Distinguished delegates, ladies and gentlemen, the latest IPCC AR6 report released in March 2023 has again clarified Africa amongst the most vulnerable regions to climate change and called for a transformational change in all sectors of society to achieve climate resilient development in Africa. According to the report, the region is projected to experience more frequent and intense heat waves, droughts, floods, storms, wildfires, and all emission scenarios. Under all emission scenarios, these extreme events will have negative consequences for human health, food security, water availability, biodiversity, and ecosystem services. The effects of the climate crisis are already dire. The report shows. It warns, for instance, that as warming continues and some regions in Africa may become more inhabitable or lose their agricultural potential by the end of this century under these high emission scenarios. The dependence of Africa's agriculture on climate sensitive variables is expected to make agricultural development in Africa more challenging because of the increasing volatility of crop and livestock yields. The net effect of these impacts is reduced food and food nutrition, insecurity, and increased hunger and poverty. African agriculture, no doubt, remains the most vulnerable sector to the impacts of climate change, and ironically, it is a sector that also contributes the most to the continent, to the problem of climate change, especially the emission from agriculture, forestry, and other land use. Distinguished colleagues, ladies and gentlemen, African governments have over the last decade and a half been implementing the Comprehensive Africa Agriculture Development Program, which is known as CAADP, as reviewed through the Malabo Declaration on Accelerated Agricultural Growth and Transformation for Shared Prosperity and Improved Livelihoods, both of which are targeted approaches to achieve the agricultural vision for the continent. Building resilience, as envisioned in Pillar 1 of CAADP, took a back burner as erosion of ecosystems and degraded water sources dwindled opportunities for the sector to respond to the vagaries of climate change. The Global Politics Prioritizing Resourcing Private Window of Global Agriculture and Food Security Program, GAFSP, rather than putting agriculture financing in a public window, is a challenge to these aspirations, and only a few African countries manage to attain the minimum of 10% of the budget to agriculture. Distinguished colleagues, ladies and gentlemen, AU and its member states continue to make bold efforts to address this challenge and have inter alia continued to put various measures in place, such as ambitious NDCs, NAPs, and other strategic policies, frameworks on climate change and agriculture. In June of 2022, the African Union Commission launched its climate change and resilient development strategy following its adoption by the Heads of States Assembly in February 2022. The AU Green Recovery Action Plan was also developed in the same year and launched and also adopted by the Assembly in February 2022. The AU Digital Transformation Strategy for Africa is another milestone in this direction. The AU in its early stages of the implementation of these critical frameworks and is actively seeking partners to maximize the impact. The Africa Agriculture Watch that is being launched today is well positioned to help the AU as it leads these efforts. The AU Climate Change Strategy places emphasis on Africa agriculture and the need to build resilient food systems and increase productivity with the potential of Africa feeding itself and the world through a climate resilient and regenerative agriculture. Similarly, one of the pillars of the AU Green Recovery Action Plan is the Resilient Agriculture pillar, and it focuses priority on inclusive economic development and green jobs. The full implementation of these important AU instruments will not only contribute to the economic development of the continent, but also support the Africa agriculture transitioning, transforming sustainably in balance with nature and the environment, lifting millions of Africans out of poverty. It's against this backdrop that the event today becomes even more crucial, as it provides the opportunity for experience sharing, build a broad inclusive participation, and digitally supporting the transformation of agriculture sector in Africa in the changing climate and making it resilient to its impacts. Distinguished colleagues, ladies and gentlemen, please allow me on this note to appreciate the partnership between the African Union Commission and Academia 2063, including that on the Comprehensive Africa Climate Change Initiative CACI project, which the organization is one of the implementing partners in Africa. Let me also take this opportunity to invite you all and your institutions to participate in the forthcoming First Africa Climate Summit, scheduled to take place from 4 to 6 September in Nairobi, Kenya, and to be co-hosted by the African Union Commission and the government of Kenya, the current chair of the Committee of African Heads of State and Government on Climate Change. Finally, I would like to assure you of the commitment of the African Union's leadership and that of the Directorate. And I'd like to thank you at this point for your kind attention and look forward to the outcomes of this event. With that, ladies and gentlemen, I submit the speech prepared for our director. Thank you.
Thank you so much, Ms. Leah Wanambua, for ably representing our colleague, Mr. Hassan Nyambe, the Director of Sustainable Environment and Blue Economy, Africa Union Commission. We take note of his very valuable contribution and kindly convey our appreciation and gratitude to him, and our appreciation to you as well. Ladies and gentlemen, colleagues, delegates, participants, this comes to the end for today, but not the end of our engagements and continuation on this very valuable topic for our continent. I wish to take the opportunity to thank all of the panelists and all of the participants who joined us across the world, and we took note of these very, very valuable contributions today. We could have gone on and on for the rest of the day, but this comes to a close. I thank you all and thank our chairman, Dr. Ousmane Badiane, and the entire academia team for a very successful launch of the AGOA, as well as a thoughtful and insightful contribution to the theme of this launch event of AGWA, which is leveraging artificial intelligence and satellite remote sensing data for decision-making in the African agricultural sector. We thank you so much. And now call our colleague, Dr. Butake, to take over from me. Dr. Butake, you have the floor, and thank you once again for all the wonderful technical work to make this possible that you have led. Thank you so much, Dr. Butake.
Thank you so much, Your Excellency, Professor Kerr. Thank you for agreeing to chair and moderate this session. I would like to echo the session chair by thanking all the speakers, all the presenters, and of course, all our attendees who joined us very early this morning to join Academia 2063 in officially launching Africa Agriculture Watch as its fourth program. Thank you for staying with us till the end. And we invite you to stand by for our post-event campaign, where we'll be sending you materials and links to the presentations from this event, as well as the AGWA brochure and fact sheet. Please visit agwa.org and take a look at the 21 plus production forecast briefs that have been published so far. Visit the platform, download, copy the citations, and of course, follow us on social media for Agua at Agua_news, and for Academia 2063 at Academia 2063. Thank you so much, and we'll be in touch with you very soon. Take care. Bye.
Bye-bye. Thank you, everyone, and have a wonderful weekend. Thank you so much.
Ciao, ciao, Prof. Great having you with us. Thank you. Bye-bye.
Thank you so much.